And thank you, Empty, for the nice introduction, and also everyone for being here and for the kind invitation. It was already the past 2 days are really insightful and super interesting. So I feel very inspired and lucky to be here. And I liked very much the format of the last 2 days. So, there were a lot of interaction, a lot of discussion. So, please, in case you have any questions or you have comments or anything, I would really love that, to transfer also to this kind of talk setting. So I don't need to talk for this full time. I mean, I can fill the time, not a problem. But, but in case you have any questions, I don't need to get through everything. I really welcome a discussion. Well, thanks all for being here. So the first topic we're going to talk about is sparsification and implicit bias. And I really tried hard to think about now this connection to Bayes-Duality, a concept that I learned about in the previous 2 days. So I have picked a couple of topics of my research interest that I think are linked to Bayes-Duality. However, so we'll talk a bit about older work like lottery tickets and how we can potentially link that, or how it has something to do with the Bayesian kind of principles, or potentially also Bayes-Duality. And as you will see, one of the big challenges that we have in the context of sparsification, where we actually want to increase the efficiency of deep learning, is that we want to basically, we also face a very hard optimization problem. So it's linked to this duality between optimization and potentially also inviting maybe not directly a Bayesian view, but some form of randomness into this concept. And we will talk about how that is linked, how we can link to implicit bias in this context that I do believe could also be present in some of the Bayesian approaches that we were discussing. And we will talk about the optimization and improve it. And if we have enough time, we will also briefly talk about more this kind of adaptivity concept that we discussed, especially linked now to continual learning. And in that spirit, we will briefly talk also about fine-tuning, so where we want to understand actually how we can, continue learning, even though it's not really continual learning. I'm aware of that, but that's the closest I'm afraid I can come now to this with the work I can present now. Okay, but let's get started on the basics. So let's talk about sparse deep learning. And as many of you probably do not need to tell anyone here that deep learning has been absolutely revolutionary, and also the principle, right? So we have a data set on which we train, for instance, a neural network to minimize a specific loss. So we formulate this as optimization problem to solve a specific task that we're interested in. However, the big problem is that these neural networks that we tend to train are huge, so absolutely massive, as are the data sets that we often need to train for these massive models with. And why is that a problem? So there was a recent trend even that that actually this problem has been amplified during the last couple of years even. So there is this trend towards always larger and larger models, as you can see also here in this logarithmic plot. So the models tend to get larger, especially, and up to a size that only industry can afford that. So we have these huge models, which means that they consist of billions of parameters. And this is now, an old version of a language model, so GPT-3. And this means that the development costs are so huge that mostly industry can afford it. And we need also large data sets because we need the compute infrastructure to do this. And even the operation costs are so huge. So from what I understood is that OpenAI currently is not even making money out of offering this ChatGPT service. So because they have so many queries a day that they need to evaluate these huge models on, and which also, by the way, requires a specific infrastructure. Oops. Okay, thanks. And this raises a lot of concerns and questions in this context. And we would like to address both of these kind of problems. We would like to reduce the development costs, but also if we could reduce the inference costs, so the operation costs of these models, it would already be a huge gain. And in fact, that is possible. So people have shown, and we have contributed with theoretical insights to this, that it's not necessary to really use these huge overparameterized models to solve a task of interest. So there exists even subnetworks of these huge overparameterized models that could solve the task with a similar kind of accuracy and performance as the original model. However, the problem is that we cannot use, that we cannot start from these smaller models to develop them, because it looks like that this over-parameterization, so having many more parameters and actually degrees of freedom that we even need, so even more than samples that we have, this over-parameterization seems to be quite crucial for the optimization, so for training these neural networks. And this is likely linked to stochastic gradient descent, so the main algorithm that we use to train these neural networks, which on its own, by the way, is rather a simplistic and a simple optimization algorithm. I was very surprised when they came from mathematics to machine learning that we would use that the main workhorse of machine learning is actually gradient descent, to be honest, because I learned in my optimization classes that this is kind of the worst algorithms you can think of. So, but of course, the other ones are more computationally so intensive that we cannot really dream of using them in the context of these huge models that we potentially care about. But it looks like that we need these huge models to actually make this work. So which means this implies if we have these dense models and we train them, we achieve usually high performance. But if we train something sparser from scratch, in general, with the random initialization, this will lead to lower performance, much lower performance. That is not really not really satisfactory. And a partial explanation of this, and I will talk about this in more detail, is the implicit bias that is actually induced by this heavy overparameterization, meaning that we have some form of regularization that is induced by this overparameterization, which explains to some degree why we don't do this absurdly overfitting that you would expect if we, according to classical statistical theory, if we use many more parameters than we actually samples. And we'll talk more about this. Before we do that, though, let's talk about lottery tickets. Just look into the problem why that is even solvable. Where does this come from even? Because what the lottery ticket hypothesis states that this problem might be less problematic than we might think. So it's actually already now an old work, and we have mentioned it already in the discussion previously, which is a work by Frankl and Gabin in 2019. They won best paper at RIKEN at this time. And what it states is, even though it's very difficult to train these these sparse neural networks from scratch, there do exist small, well-trainable subnetworks of large, randomly initialized neural networks, and we call them the source networks. So it means like we can, wrong direction. It means like there exists a subnetwork here that when we train that from scratch with exactly the initialization that we obtained by pruning this neural network, we can train this to completion with the same algorithms that we use for training the large model here, and we achieve the same performance, or roughly a comparable performance as that we would get if we would train now this random overparameterized source network. So there exists also an initialization that would allow us to train these neural networks. And they also proposed. I understand what that meant. Yeah. So, what that.
You say, well, trainable subnetwork of large, randomly initialized source neural networks.
Exactly.
So you take a large network, you randomly initialize it, then you're saying a subnetwork of that is trainable.
Exactly. So I still need to train it, and then achieve a good performance. We will go further, though. There's also a strong lottery ticket hypothesis. We'll talk about it in a minute, which would even imply that we do not even need to train anymore. So we can only prune even and achieve a good, well-performing network.
It seems like universal approximation theorem. Like it's possible, and we know how useful it is, right? So.
Okay, you actually let me, if you want to, you can skip a big part of the story when you want so, because yes, it's true. These exist. But exactly the pruning algorithm, or pruning to find that is NP hard, and even NP hard in a way that we do not have pruning algorithms right now that will, do exactly, find these great lottery tickets in complex contexts. Okay, we'll get there. What is interesting, hopefully, to some people that are Bayesian, or I thought at least what's interesting is here, notice that these parameters are drawn randomly. So they follow a random distribution. Maybe you think of them as a prior or something like this. And the only thing we need to do in training is masking. And what we can do is there exist algorithms that would also do this. The algorithm that has been proposed to find now this initialization is in still interesting context, but not that large scale. This was called iterative magnitude pruning. And what you do is you train a neural network to completion, then you prune let's say 20% of the parameters away, so you keep 80% of the parameters according to magnitude. So you keep the large ones. Then you rewind all these parameters, the ones that you kept, back to their initial value. So some of them stay 0. The 20% that you removed, they stay 0. But all the other ones, you rewind them back to their initial value. And then you start training again. And you do this iteratively again and again and again until you receive something sparse. And the goal, this means what you do in the course of this algorithm, you identify two things. One is a mask, and that's quite important. We actually learn the mask. And we identify also an initialization that allows us to actually train this thing from scratch. Spoiler alert, that of course, this contains the mask and the initialization though. This will contain information about the data set and the task. So this is not completely random or something like this. Finding that is now computationally hard, and it's not trivial for that reason, and not something you can do easily. So the problem though is that this does not work that greatly in settings where we that become very complex. So if the models become too large and the data sets too, let's say, heterogeneous, this is not absolutely that greatly working anymore. So what has been proposed instead is learning rate rewinding. This is kind of state-of-the-art results that it actually achieves now. Something very simple and what you think is more natural if you don't think about lottery tickets. So you do the same thing, you train the neural network to completion, then you remove the 20% of the parameters, but you do not rewind the parameters back to their initial value, you just keep them, the ones that you have learned, and you start training from there. And you kind of think this makes more sense because, we keep the information, we spend a lot of compute on this, right? We keep the information that we have identified already before, and we just compensate with the next training round for the performance loss that is due to the pruning. This is called learning rate rewinding. So it does the same thing, but it does not rewind the parameters. So this achieves higher accuracy, but this is computationally expensive to do. And there are many more different algorithms, by the way, that have been proposed to solve kind of different trade-offs in this context that also try to identify now this sparse neural network structure that at least should have lower inference costs in comparison to this large model. Among them are dynamic sparse training, the lottery tickets that I've talked about, continuous sparsification, compression, and distillation. There are different kinds of types of methods that try to achieve a similar goal. And we will talk specifically a bit more about continuous sparsification in this context. The problem with all of that is, though, note that the compression ratios that we can achieve are limited, first of all. So we might end up with 1 to 10% of the parameters. We still need to keep them. Sounds like a lot that we can throw away. However, remember these models that we start from are also massive and huge. So it's not really fundamentally solving our problem. It helps, but it's not like, big breakthrough, if you want so. And we need a large model to start with, at least. It means we need to train at least once. We still need to solve this problem of training this over-parameterized model at least once. Usually need to do this multiple times. And variance. So we'll talk about this. But big problem also in this context, we have talked about it already, it gives up on the lottery tickets. And the question is that really necessary? And you have talked already about it. No, of course it's not. In theory. So in theory, these things do exist. And we can briefly talk about it, but why that is even provable is because there holds a stronger hypothesis, and this is a strong lottery ticket hypothesis. Namely, we do not even need to train again anymore. We can really just take this random network, this large random network, and prune it, and then receive, a network that performs already really well. Meaning, we only need to identify the mask. This is a binary kind of thing. It's either 0 or 1. 1 means we keep the parameter in the network, and we keep the random weights. But in comparison to now the Bayesian approaches that we have talked about, here the randomness is kind of frozen or static, if you want so. So we don't redraw that in the course of training or anything. So the mask, because we need to really, the mask has meaning only in the context of the frozen given weights. Okay, how does this in general look like? It's really just an expressiveness statement of the form like. Let's assume right now, and this is a big assumption, by the way, there exists a target network. So there exists somewhere in this beautiful world, there exists a neural network, a smaller scale neural network that can solve my task of interest. And this is something I usually do not have access to. This is what I would like to find, but I do not have access to it. And what these lottery tickets existence statements tell us is that, we have the source network. This is randomly initialized. And if I prune that, so identify a random subnetwork, I identify a lottery ticket, and this lottery ticket can now approximate this target network. So it can be presented a similar function. However, notice something here. I've already suggested that in the visualization. This lottery ticket here is wider and potentially also deeper than the original target network, meaning we cannot expect to find something optimal in that sense. So there likely exists a better, sparser function, or a sparser neural network representation of that function that I care about. However, with lottery ticket pruning, I likely can only find something that is sparser than the source network, but not as sparse or small as I would like it to be, potentially. And the statements are then of the following form. So it means, like, I assume I have this target network, and now I wonder how much wider does my source network need to be in comparison to my target network, so that I have with high probability, with probability 1 minus delta, I can find now a good approximating lottery ticket. And what is interesting here is what this says is, so this is here the width, if you want. So the source network width is here highlighted in green. This is, we find now a lower bound on this, and or a bound above which we can guarantee existence, roughly with probability 1 minus delta. What you see here is that it's only wider by a logarithmic term in the relevant parameters. So logarithmic in my failure probability, logarithmic in my approximation property, and also basically other kind of parameters that are related now to the number of target parameters. And logarithmic is great because it means, like, it's not that bad. It doesn't need to be much wider. In practice, that roughly means by a fact, we need to be 10 times wider than the actual target network, by a factor of 10. And that's not bad. And that also means, like, these lottery tickets should really exist also in these complex settings. Interestingly, but we don't even need to start from this random source network that is dense. We can also start from something sparse. Think of that with probability p, now this edge exists, and with probability 1 minus p, an edge does not exist. It's called an Erdős-Renyi network. We just drop edges randomly from the start already, independently at random. With this probability p, we keep them. And we need to pay, of course, in terms of width, but this explains why we can even start random, and we never need to train a large network from scratch. So with random pruning, we can get relatively far already from the beginning, meaning, like, dense, we really do not need to train a dense network usually. We can, but there are limits to it, because unfortunately this is also necessary lower bound, and that means, like, we can maybe go up to, let's say, 80% sparsity or so with random pruning, but not go beyond that. So we will still need to prune within the source network if we want to proceed from there. But a lot of these iterative pruning steps that we have in iterative magnitude pruning or learning rate rewinding are not necessary. So they are obsolete. So we don't need to go through them. This is good news. And since we had a discussion yesterday about it, I also included, a small statement about universal lottery tickets. Also, those exist, by the way, because we were wondering to which degree can we transfer. We were talking also about transfer learning, and to which degree is that possible. You can also expect that you can reuse some of the lottery tickets that you have identified and transfer them to new tasks. However, very important in this context is only up to some sparsity level. So we cannot make them super sparse. If they become very sparse, they become specialized tasks. And if you want them to be still adaptive, and so that we can actually transfer them to new tasks, so if you want them to be still trainable to some degree, we can only go to moderate sparsity levels. Interestingly, similar ones, that we could also, that should be sufficient for random pruning. So there is something to gain from, from kind of transferring these lottery tickets, but we need to be careful to still keep adaptivity. Yeah?
Sorry, yeah. It's an important point, so I just wanted to understand this. Are you saying sparsity hurts adaptivity?
Yes.
Okay.
It does. And that's linked to this, the problem of trainability. So these initializations that we find, for instance, in the course of lottery ticket pruning, they also contain information about the task. They don't make them universally well trainable suddenly or something like this. It's not because they make them trainable because they come already close to a solution in some way. And we will also talk about what the exact important ingredient is of that. We will learn about this, that this will be related to the science of the parameters. But on their own, something sparse is less well optimizable if you want so.
Okay.
Something very sparse.
So these proofs I don't see, so I just wanted to understand, like, how much should I trust it? Why should I trust it, maybe? Like these statements that you're making.
Yes.
Like, under what assumptions they hold, and how do you make these
kind of the lottery ticket existence? So they assume, so the most crucial assumption is, like, I assume that there exists a target network. But otherwise, I can really say, like, so I'm relatively flexible in the distribution, for instance, of the weights of my source network. I'm relatively flexible in by the way, this holds for all kinds of targets of a certain width. So it's not just, for one given target, but once I have the source network with high probability, I can represent all targets of a, certain size that are smaller than, by a certain factor in comparison to my source network even. So, but these are existence statements, right? These are not statements of the form like I can find them with stochastic gradient descent. And that's very important.
Right.
Yes. Yeah.
Another question. For this universal lottery, is there, maybe I'm anticipating stuff, but is there in the proof of existence any assumption on the, let's say, similarity of the different task distributions? And also, I guess, like, is there some kind of bound, like we've seen before, where we have not just the width of the target networks, but also how the bound grows with the number of tasks?
So how it works is, so I haven't shown you the details here, but it was a great question. So how it works, actually, so the main line of reasoning is the following, namely that you, with this kind of normal lottery tickets existence approaches, with a bit more generality here, you construct in the end a basis function, a set of basis functions. And you do this, by the way, by going back to some kind of Kolmogorov-Arnold formulation. So you basically say, like, I have a specific kind of functional form of my basis function that is very general, this Kolmogorov-Arnold representation, which consists it uses specific univariate functions. Probably it doesn't matter too much for your question, actually. So I have a specific construction for common basis functions. And now I can represent a function family that is essentially linear combinations of these basis functions. And this is the main reasoning how it goes. So it's very straightforward in that sense. So I can only represent my tasks basically need to be solvable by a linear combination of this kind of basis functions. Yeah, and the more basis functions I need, the higher is also my width requirement. It scales with it.
So the assumption on the task similarity will be in terms of, let's say, the coefficients of the basis functions, like how they relate.
Yes, exactly. The approximation quality, essentially, of my function with respect to these basis functions.
Okay.
Exactly. So this is a kind of straightforward, probably, way you would think about it in the context of even, functional analysis, I would say. Yeah, exactly. Okay, so, but we have not solved this problem of adaptivity here in this context. So these were kind of empirical kind of observations that you cannot go too sparse with these things. And the reason is also because then you lose the theory in support of that would say, like, so if I have fewer basis functions, also the family function class that I can represent is less rich, right? So it's a smaller kind of subset. So I'm also not that well adaptive to other kind of tasks, because the whole class of my tasks that I can represent is smaller in many ways. But it's not directly related to the optimization, because the optimization would become very easy here in this context. We just need to learn this linear combination. So, but now the question is, in this context, why don't we find the lottery tickets then? I told you they exist. And, but we have even, we have constructed a best test bed where we show that we really need better pruning algorithms. So the problem is the pruning algorithms, iterative magnitude pruning, that doesn't find these lottery tickets. Or also edge pop-ups, so a different kind of pruning algorithms that could even find these strong lottery tickets. So in this context, let's now look into a specific kind of algorithm, because we want to improve these pruning algorithms. And we look specifically in continuous sparsification and the implicit bias it induces. And the reason for that is is that I do believe it also has an interesting relationship to this Bayes-Duality principle, and also because I think it's a good way to approach the problem. But okay. But we face two main challenges in this context when we want to improve these pruning algorithms now. So we need to do two things. We need to do structure learning, so we need to identify the mask, and we need to somehow train these sparse models from scratch. So the more we sparsify, the harder becomes the optimization in many ways. So we need to learn, basically this means we need to learn the M and the W. So the weights and the mask. And this is something that continuous sparsification sets out to do, as other pruning algorithms as well. And it is based on this paper here. And interestingly, I should say it was at the same time. That comes a bit later. We'll talk about it in a moment. Okay, so let's see how that is related potentially to some kind of Bayesian approach. It's not really directly the same. However, it might remind you a bit on variational dropout, because also that sparsifies deep neural networks. That's a seminar paper, I think, from 2017, where they also have shown this. So that was even before the lottery ticket hypothesis, and was post. And what is happening here is they learn a mask in addition to the weight parameters. So we want to learn this M times W. This will be our final parameter that is used. And it can be interpreted as variational dropout when the learning, basically we learn the probability P that the edge is not masked. So with probability 1 minus P, the edge is masked. And you could do this also in a totally Bayesian kind of setting. In continuous sparsification, though, you will want to promote or anneal these probabilities to become either there's missing a part to become binary. So we want it to be either 0 or 1 or something close to it, and then we set it to 0 or 1 in continuous sparsification, because in the end we want something more static and not necessarily that probabilistic. In that sense, it might be less good for uncertainty quantification, because we actually want to be relatively certain about the edge. This is continuous sparsification, and many approaches in continuous sparsification are of a similar form. So they will find some form of continuous parametrization of this probability P, and then try to send it to 0 or 1. And what means is we learn actually a parametrization of M, the mask, and the W jointly. So we can also join, and what we found now is that we can also learn just the product M times W. Usually the M is constrained. It's somewhere between 0 and 1, for instance. Let's think of a sigmoid, or so, you use a sigmoid or a different kind of parametrization of this M. However, we can even assume now that this mask M can attain any value in R, essentially, so any real number. And we can still have a sparsification process going on if we learn M and W jointly. So the product M times W instead of the original weight. And that's interesting, because we can even get this. So continuous sparsification has an implicit bias going on its own that sparsifies on its own already. So it's less about, we need to care less about sending anything to 0 or 1. I have a complicated annealing schedule necessarily for these probabilities. However, what we have to do is we need to combine that somehow. So we have an implicit bias. I will tell you about it also in a moment. Yeah.
What differentiates mask from the weights?
In this case, nothing. It's just like it's really only inherits the structure of this continuous sparsification approach, that we have a mask times a weight value in this case. But here they are completely, on the same level.
But one may argue that you have increased the parameters.
Absolutely true. That's a problem. We will solve it later. But it increases in memory.
Because then if you compare in your experiment, then I'm sure reviewers have said that to you.
Yes.
You should compare with their double size network.
Absolutely. Absolutely true. And however, it depends a bit on the context whether this memory is actually relevant, because often dominating in memory, especially in vision context, is not so much the number of parameters, but actually the activations that you have on batches. So it's actually a small share of the memory in that context. It becomes more relevant for language models because the parameters are more, the number of parameters are more dominating in comparison. But yeah, different problem. It's true. We'll solve it though, but not yet. So bear with me, because first we want to understand the structure of it. So here you have it already. We have this But we have now double the number of parameters, which means we have a source of overparameterization, and this also means an implicit bias. The only problem that now is that an implicit bias is usually something that's induced, let's say, by the parameterization on the architecture, the optimizer, but it's usually not something controllable. It's just given. It helps you potentially, but you do not control it. But in this context, if you want to use it for sparsification, we actually need to control it. And as a side note, at the same conference, I think at the same time, David Rügamer and his group, right, also published a paper that is highly related. So you can also not only look at the product of m times w of two parameters, but actually also at the product of, of basically more values, if you want so. And they have also recognized that if you combine that with this kind of weight decay on these weights, that this is an equivalent to kind of this regularization that you can see here on the side. So you can also solve this optimization problem on the left. In asymptotically, so the solutions of one will also, be solutions to the other problem. In contrast to this, though, what we focus on here is a different kind of notion. What's really important here is that as you can see here, is this weight decay is controllable right now, because we can change now, and it's crucial for our results, is we can change now the strength of the regularization during training. And that means, and this will be our means to control the size of the implicit bias, because the implicit bias does depend on this regularization strengths. And this way, we make now this implicit regularization controllable with explicit regularization in a different kind of space. And why do we need that? So, probably what we found now is that the question is, of course, how should we change this? And what we found is that this exponential decay is actually quite good for an exponential weight decay is kind of what worked best to schedule now this kind of regularization. And that is very similar when you think about it to these pruning algorithms that we had, because also they would exponentially kind of decrease the number of parameters. And that seems to be really good also in the context, of this sparsification. And the question is why that is. And the reason for that is we will look into in a moment in the nature of this implicit bias, how it looks like. And we also have a result for that. Don't worry too much about it. You don't need to understand the details here. It's only in terms of structure. We have a result of the following form. What you see here is this R to AT. This is the implicit bias, if you want. So this is a Bregman divergence that is implicitly now optimized in the space of the original weights. So think of this as a parameter x that is equal to this m times w. And we want to understand right now what happens in the space of x. If we would do the optimization in the space x, how would that look like? If we wouldn't do the optimization in m times w, we do the optimization in m times w, but doing this in mw implies that we induce now different dynamics on x. And these dynamics on x mean that we have here right now an implicit. So, but what it means is we have now dynamics in x that are guided by this Bregman divergence. And this Bregman divergence now, so what you could take away from this one here is now time dependent. And this describes now this implicit bias. So also implicit bias is changing over time. And that is crucial for the result that we can actually, first of all, we can control it with this explicit regularization, because it depends exactly on this alpha t, our regularization strength. But it's also important to actually make the sparsification feasible to achieve good results. What we see is that this Bregman potential actually changes from an L2 regularization in early training rounds to an L1 regularization later on. So we don't have, people would usually just say, okay, we have an implicit L1 bias, but it's very, very important is that it changes from L2 to L1 during training. It means like in the beginning of training, we can still train an almost overparameterized neural network with this L2 regularization. So we learn something really good with the help of this other kind of remaining overparameterization. And slowly we we tell the network we want a sparser solution by going to L1 later. And that means that we can still achieve high performance earlier and then try to get sparser once we have this reached that relatively high performance already.
Can I get to know the previous slide, the expression a little bit?
Mm-hmm.
So it seems the bottom you're saying that, there's D and then there's also nebula, so I'm a bit confused, but I suppose you're saying that the mirror flow somehow matches the gradient flow?
Exactly.
Is that what you're saying
Yes.
at the bottom? Okay.
Exactly.
And then the mirror flow, so where's the dynamic part? Like, sorry.
So this is kind of the dividing dynamic here.
So,
You see this? I probably have a.
Laser pointer, is there a laser pointer there?
There should be, right?
Maybe we should look at this. Yeah, I think we should get the laser pointer somewhere.
There's another one. Ah, nice. Thank you.
It's probably very weak.
Yeah.
Okay.
Yes. So this one here.
Yeah, so that I understand. But then what is the so alpha or something? You have the subscript there. Okay. Yeah, sorry, I'm old.
This one here. This
Yeah,
AT.
so there's a
Yeah, the problem is
subscript, right?
it's not really nicely. So we have an alpha and an A. That's important, unfortunately.
And
They're different.
I
And in the
cannot see
details.
them.
So what you see here is, so I can go in a bit more detail. We have also a framework paper that explains it in a bit more detail. So this AT here, what you see here is alpha is the strength of the regularization here.
Yes.
What you can see is it accumulates over time. So we have an integral here that goes, basically the whole regularization over time impacts now the actual strength, of this AT that now determines the Riemann divergence essentially at this time. So let me see. Yes. Here, this R, right, is here. This is the important function. I mean, we do take then a derivative of this. But
So,
what you
so
can see here
you
is
said you have I sums from 1 to n, and what is that? Is that data or?
I.
So there's a sum in the R, right? What's that sum over? What is the I?
I mean
over?
this one here. So I think this is about the different kind of. Let me think about it. Good point. This is about kind of the, you have multiple parameters contributing to it.
I see. So n is the size of the parameter. And for every parameter, you got the thing?
Yes.
Okay. And then for every parameter, you got an A. And that is an accumulation.
Exactly.
I see. So I'm just trying to understand what is time dependent. So time dependent, where does
So the alpha. So it's a bit complicated.
Yeah, sorry.
So
I
we
see,
add
because
at
it's
time
an
t, and this
accumulation.
integral goes to t, exactly.
I see.
And we accumulate now all the regularization until this time to be actually in the strengths, to control the strengths of this this Riemann divergence. And that's really important because I didn't talk about this in detail now. That is important because you have this accumulative effect of this kind of control, meaning that what you can even do is, and we have that in a different kind of paper, we'll briefly mention it later, is what you can do is you can even switch off regularization at a later point, which is actually also good for convergence. So at the end, you want to even switch off, this alpha t should go to 0. And you still have this accumulated effect of, that you will still go towards sparsity. So you have a kind of memory of this if you want so. It's not really memory because it still impacts, the whole, it impacts the regularization strengths at this later time. We call that accumulated effect, in lack of a better wording.
Yeah, I think it's more clear now.
Okay, awesome. Thanks. A great question. Yes, and this accumulated effect, though, is really crucial for getting then to this L1 later. So you can, and what matters at the beginning, what you do at the beginning matters also for the strength of this L1 regularization later. But yeah, main takeaway here is that this Riemann divergence now is controllable in a complicated way, though, with this cumulative effect, right? And we can transition now, and this changes the dynamics overall. So we have this memory of regularization that I was talking about. And we go to L1 long term. And but this is not the only thing that's important here. So we can get these kind of convergence statements, also for more general initializations, but also the initialization is important for making this work really, in good settings. So make this well optimizable if you want so. And we also propose now a specific initialization that shows then in the context of sparse linear regression, this is a toy example, that we can really get much lower error. And we can and exploiting this, of course, we can also do this now, I think, in the context also of I think this is CIFAR 10 and CIFAR 100 right now, but also in terms of ImageNet, this really boosts the performance of this algorithm by a lot. And we do not need to, this is not, we don't train this neural network, we train this kind of once, if you want so. And we can also get relatively early already some form of sparsification that one could exploit also in the continuous of learning. So it means it lowers the development costs to some degree, at least a bit, and it achieves still a high performance. And we also have a more general kind of approach to this. So where we explain in a framework how we could use also different kind of parameterizations and then derive the implicit bias by it and how we can control this implicit bias. So what's the effect of this kind of more general kind of regularization here? So if you have a specific kind of optimization that you care about, this F here, if you have now this more general F here, there are corresponding regularizations now that will nicely make this whole thing work out so that we can induce a mirror flow and then get this Bregman divergence. So for this F, we can find also an H, a regularization and parameterizations so that they can work together nicely and induce these mirror flows so that we can derive this implicit bias. And that's kind of relevant because we have kind of three effects that we will talk about. I mostly talked about the type of bias changing, for instance, from L2 to L1, but there are also positional bias and range shrinking that you can also try to control with this. So, but let me go a bit more quickly then about the training and optimization. And I think I will, so our main goal now is to train things ideally from scratch, sparse things. So that's also the goal of my ERC starting grant. The main goal is to now improve the optimization. And I promised you at least, and we'll run through this a bit more quickly. So we want to understand what makes this optimization actually hard and how the overparameterization is helping these kind of sparsification algorithms. In this case, this learning rate rewinding that I was talking about. And I will go through this now quickly in the interest of time, sorry. But we have a theoretical framework that helps us understand this. It makes it very intuitive. I will just give you the result of this now, though. So what it says is that what really is crucial in the optimization, so what these kind of those algorithms, learning rate rewinding, or also plus overparameterization is good in comparison to something like iterative magnitude pruning, so the lottery ticket stuff. They are good in flipping signs. So here we have two kind of weights. Think of that as a two-layer neural network, a very simplified one, where we have inner weights and outer weights, the A. The inner weights is W, the outer weights are A. And what it is good at in specific situations, so if the signs are correct in comparison to a target problem, of course, it doesn't matter, what we do. Lottery ticket stuff and so on will be as good as this other learning rate algorithm. But something like learning rate rewinding uses overparameterization to flip a sign. In particular, what it is good at is now if the W is wrong, so the inner kind of sign is wrong, it is able to flip the sign in the course of training and then use that better sign in the retraining process again. That is why it will be good also in training something sparser from scratch, if you want so. So what's absolutely crucial is, and I'm sorry I don't have time to convince you now of this in detail, but we have studied that in more detail with ablation studies, is what's absolutely crucial is what we need. Well, I can show you the table because it's much more general. So what we have shown here for more different kinds of sparsification algorithms here. So these are kind of different classes of algorithms that we've talked about. ACDC, Riegel, and STR. These are all kind of state-of-the-art algorithms in their respective kind of category they have different kind of approaches to sparsify. What we find for all of them is they are good in identifying a mask, so that works well, but this is not the main part that they are doing. So if we would take the same mask that they have identified that we know works well, so the same structure, and we randomly initialize it, we do not achieve good performance. But you can see here in the bottom here, with this random initialization. But this one here is the baseline performance of these algorithms. What you see is there's a drop in performance. This is now an ImageNet here. So if you would randomly reinitialize these sparse structures, that's not good enough. Yeah?
Random initialization, meaning that we use the random weights, or we train random weights?
We do train with the random weights. So we randomly initialize and then we train with SGD, or, we even try a few other tricks, to improve the optimization. So what this means is just identifying the sparse structure is really not sufficient. So the initialization that they learn is also in some sense, also somehow they learn also good weights in the process, and this whole sparsification process is important for them to achieve this high performance. And what we found now is, if we look now just at the signs of the learned parameters, and we use those and random magnitudes, we can actually train them in a way, so here the finer signs, to achieve basically competitive performance with the original performance. So only the signs contain the relevant information. Everything else SGD can do, but the signs are the ones that they really identify. And interestingly, it's not even the finer signs that are necessary. Even after something like 30 epochs, the signs are already sufficient. The signs that I learned after 30 epochs or so relatively early, these signs are also sufficient for SGD to do the rest. Yeah?
30 epochs out of how many?
30 epochs out of, that's 100 in this case. Yeah, so roughly 1/3. One can even try, yeah. And magnitude, doesn't do the same trick. So really there's more valuable information in the signs. Okay, so we have identified kind of the problem, if you want so. What we need is...
Is it specific to your setting, where like you do mass times the weights and then that specific regularization?
No,
it's a different one.
Different one. So for continuous sparsification, that would also work. So it also is good in learning the signs.
Okay.
Exactly.
Yeah.
Now it's more general in kind of the question, what makes the optimization up? Sorry, I skimmed through it. Yeah. So what did you want to do? So it's a good point. I should, really explain the problem. So I want to understand right now, what do I need to do to make something, to be able to start from something sparser? So I want specifically to improve the optimization. So I want to be as sparse as possible early on during training. And the problem that I have with that is that I do not know the signs of the parameters well. So basically how they are coupled, how they need to be coupled to the mass that I have to do the rest of learning. So for instance, with SGD. This is what we're saying. And so we need to learn these parameter signs in some way or identify them. And now coming back to the continuous sparsification that we're talking about, this pilot method, with this M times W, interestingly, with the right initialization, there the initialization is crucial, so we need to reinitialize during training, we have an implicit bias that allows us to actually do the sign flipping. So at least if we combine that with overparameterization, so we are still not there yet, cannot start sparse, but in principle, in theory, if you overparameterized in this theoretical setting that I've talked about, we can solve all kind of cases, of initializations that I was talking about. So it solves our, theoretical test bed, I should say, right? Doesn't mean it solves everything. Right?
What is A?
A and W, I didn't explain that in detail, is I had a simplified setting where I want to train one value, essentially. One neural network consisting of 2 layers with 1 neuron in it. Absolutely simple. But it showed us already, the limits of what these algorithms can actually do. And now, if we train now with the parameters M times W, though, in principle, we can, so if you would combine that with learning rate rewinding in this with this parameterization, we can solve the problem. So we are better in sign flipping, essentially. So, but we still have this problem of this increased memory, and it's also not super stable. So what we can do is we can design a better optimizer as well. I know. And now I made this connection. I wanted to make this connection to your Bayesian learning group paper, where you basically propose that in this optimization, we can achieve good, basically natural gradient descent if we choose the right Fisher matrix for the update. The problem is that I don't know exactly how this Fisher matrix now looks like. It just has a similar form, what I'm proposing, because we somehow want to rescale the gradients. And if we do that, now specifically with an exponential kind of update, what you can see here, that depends on the signs of the updates and those previous gradients, we can do it. So this has now exactly the same implicit bias as this M times W parameterization, but it does not need to actually explicitly do this overparameterization. It just has the same implicit bias, but we can train in the original parameter space.
So X here, is it M or W? Or?
X is now M times W.
M times W.
Only that we never need to train M times W separately. It's the original parameterization. It's the original weights of the neural network, if you want, so the parameters of the neural network.
I see.
Yeah.
xk plus 1/2.
Yes. So what I haven't shown you here now is that xk plus 1/2 would just be a regular gradient update. So this is what I would receive after one step of gradient descent. But I don't exactly do that step. I do scale it with an exponent of something like the gradient, and that is signed, kind of. And what it tells me now is intuitively is it does something different when I come close to 0 versus when I'm far away. So when I want to come close to 0, I actually want to promote to flip the sign. So if my parameter itself is small and my gradient points towards I want to go in the direction of 0, it basically tells me it's okay to go there and to flip the sign. This is what this is kind of saying, because that is what I want to do. Usually the problem is the gradient descent has really a problem flipping the sign, going through 0. It gets very slow there potentially. And I just want it to flip then, if all points are pointing towards I want to flip, essentially. And I want to do this faster. And what this is doing is, and what we were really excited about the results, because we were not expecting that this would work so well in terms of optimization, it is also good just for dense optimization. So if you compare this right now, it's unfortunately, the notation is pretty bad. But they insisted, unfortunately. So we have a baseline performance here. So this one here would be if you just train a neural network on ImageNet here right now, ResNet 50 on ImageNet, baseline performance here. Now, if you use our regularization with 100 epochs, not our regularization, our optimizer here, we call it HEM, you get a considerable performance boost just with dense training. If you do that longer, you get a larger performance boost. And you might be aware with a sparsity aware optimization, SAM, which is really good in boosting performance. So it's actually something you can do always. It's just a bit expensive. So one gradient step usually is as expensive as 2 gradient steps. There are kind of ways to try to get around that to speed it up approximations. But in general, you can think of that as being more expensive. And if you train that now for 100 epochs, you get something actually quite a similar kind of boost as we get with HEM. But what's nice is that there's really a different principle behind the sparsity aware optimization. That means we can combine that with with SAM and HEM and achieve an even higher performance boost. And this is just dense training. This also nicely boosts all these kind of continuous sparsification approaches, other kind of sparsification approaches, even training from scratch. So if you train something, so this would be called pruning at initialization. So it does improve all of these kind of things. Now that we have improved the optimization, that is now training from scratch, essentially. But we have different training phases. And what I argued already about, that likely we need different kind of regularizations in the beginning rather than in the end. And for that reason, I would also like to talk just about fine-tuning at the moment. And especially because it's also related to the adaptivity. This is a new work where our main goal is now that we want to, basically increase the adaptivity of fine-tuning and still reducing, let's see if that works, an animation. So we have usually this problem of that we want to use the foundation model and train it on different tasks, and something is, okay, good, there it is, sorry. Okay, so we have the problem is that we want to use it on different data sets and adapt it to potentially different tasks. So this fine-tuning needs also to be relatively adaptive. However, we would like to make this cheap, potentially, and also improve the optimization. So we could also just train a subset of the parameters of this foundation model. And then the question is, of course, which of them? So which are the plastic ones, if you want, so the ones that are easily trainable, that can change during training? Which ones are the important ones and that can keep, and so that we can keep them to avoid catastrophic forgetting? And maybe all of this even has optimization benefits if we pick the right subsets. And it unfortunately doesn't show very well. You can't see it well. But we just pick a subset here of the parameters of the foundation model. And what we found is, interestingly, is that when you look now at the absolute value of weights versus the value of the gradient, that during fine-tuning tasks, we have a very, it looks like something, we have a strong correlation here. We have this kind of, we call this, we have this kind of very clear shape, as you can see here, that looks almost like a cross. And what it means is that the parameters that are small weights tend to have larger gradients. And that's mostly true for fine-tuning or in late training phases. This is not so true for when you would train something from scratch. You would, this is usually more of a plot that you would expect if you train from scratch. So there's a less strong association between small weights and large gradients. But during later stages in training, it actually becomes clear and apparent, and it's especially strong in fine-tuning large language models. However, it's really not exactly the same. So if you would pick now the weights, only a small subset of weights, let's say 10%, 1 to 10% of the parameters that we want to train, and we focus on the ones with large gradients, this would be here now, for instance, the red ones here, okay, this would be 0.001% gradients, the top ones, are not the same set as the ones if you would pick just the smallest weights. And that's quite important, because as it turns out, you could ask the question, what's more important, right? Do you pick small weights or large gradients here in comparison? Is there a difference? And what it turns out, if you just pick the small weights and not the large gradient criterion in comparison what people would, what you would actually think is the best adaptive, these are the best adaptive ones, we do get better results with small weights rather than large gradients. And the reason is that we can avoid catastrophic forgetting better if we focus on the small weights. Because the small weights are the ones that didn't seem to be super crucial for the pre-trained task. So these are the ones that we can safely change to some degree and adapt to the new task without forgetting what we have learned about the pre-training task so much. But if we would also change now some of the really important weights with respect to the pre-training task, we would actually induce a much larger change of the foundation model in comparison, on the new task in comparison to the old task. And this is actually what we potentially want to avoid during fine-tuning. So when it comes to, as we discussed already in the last days, is when we want to learn something new, when we want to do continual learning, it's not only about being adaptive, it's also about keeping as much information as possible about, or the relevant information about what we have learned already in many ways. Yeah.
So the difference that I see between small weights and gradients is that the gradients need data, right? So are you taking the gradients on the pre-training data set or the fine-tuning ones?
That's also really interesting, exactly. So the gradient is with respect to the new task. So the new task, yeah, exactly. So the fine-tuning data set. But the small weights are kind of more universal if you want. So we don't even need to look at gradients. It also means that algorithmically we can use that to reduce the memory of this.
So you've seen for different fine-tuning tasks, there's this correlation, as you said.
Exactly. And this is, where is it? I thought I also, yeah, there it is, actually. So we have, you see here an average performance over multiple tasks. And across many different tasks, it seems to work better to focus on the small weights in comparison to the large gradients. And we can also train then with a larger learning rate and speed up training, which is also nice. And so it's also more efficient and also more memory efficient in comparison to something that focuses on large, this would be here microatom, that would focus on large gradients.
And last question, in terms of sparsity, how many weights are small? Let's say, how many do you actually get to optimize?
That depends on the model, but we usually pick something like 1%. Yeah, which is kind of nice. I mean, this one we already had the summary, but it looks like we should head directly towards the discussion.
Yeah. Sorry, so we have only 2 minutes left. Okay. So, and it would be nice if somebody other than me and Julia would ask a question. So, anybody?
Yeah.
I wanted to ask how many small weights do we have in our network usually? I mean, the percentage, because.
So in general, we have, so it very much depends on the task, right, and what you consider as small. So depends on, where you put your threshold here also. So what is small depends a lot also on, what do you want to keep. So it depends actually on the old task and the new task in many ways, right? What the right threshold is for deciding what's small. But we could go fairly well with 1% of the parameters on the task that we studied. But you could likely also train more of them. You can also, do full fine-tuning, and that often works, right? So you could also train in principle all parameters. It's just But if you want to optimize it, this will likely, unfortunately, it's a hyperparameter. It's a hyperparameter in many ways. If you want to really optimize your result with respect to this threshold.
I see, because in the next slide, I was looking at the random weights performance, and it's a bit strange that if I pick weights at random and the small weights are only a very small percentage, how come we still get such a good performance?
Okay, so this is the percentage of parameters that we could train, and we wanted to minimize. We didn't want to train many parameters at once, but in principle there are more small weights. So when you look here at these distributions here, you could also say like, you have a cutoff. Let me see here. You could also define something like this one here is so small, everything is there, and this is a larger percentage of the parameters. I don't know exactly now in terms of quantile what it was exactly in this context, but there's much more small if you want so. So usually when we do sparsification, we could likely remove 90% of the parameters, at least in this context, without harming the performance much. Thanks.
The small weights have large gradients. Does that mean they're really fluctuating during training? So then maybe one could look at some kind of signal to noise ratio that would be the Bayesian thing to do, not only look at the magnitude, but the magnitude divided by the variance, something like that. As a measure of plasticity, have you thought about this?
Yeah, that's nice. We have done that in a different context. I don't have the full results yet for that, unfortunately. We have looked into this in the context of, because we also want to exploit this kind of insight in the context of sparsification, which is a bit more problematic because we have these different kind of training phases, and we likely need, and what is important changes in the course of, if you train from scratch, essentially, something sparser from scratch. And there we have looked into this, and there it's not that clear that it's just the small weights that are plastic. So it depends a lot on this kind of phase. And also, if you want to prune, what's kind of relevant for the site. So I can't tell you exactly, but it's a great idea and definitely important.
Okay. Yeah.
Thank you.
Yeah. And the second question, sparsity in the talk was with respect to the unit basis, but it would also be interesting to consider like a subspace sparsity with respect to the space spanned by the gradients. Have you looked into this a bit?
So there is other work that has kind of looked into kind of subspaces where you learn. So there's some interesting work, for instance, that tries also to understand how much information kind of is in the initialization and in the actual mask when you do the pruning. And they kind of make this argument that after some point in training, you hit kind of a linear subspace, and you can only continue learning in this linear subspace, and you will just hit then your optimum. So it's kind of related to the shape of the loss landscape. But it's definitely something we are looking into and that we want to find. We are searching for parameterizations that allow us to learn much more lower dimensional, not actually higher dimensionally, instead of making it higher dimensional, we would love to make it actually lower dimensional in the training. And I think that's the right approach to go. It's just more difficult to understand. You probably need to learn where you need to, what is the relevant subspace to optimize in.
Thank you.
Cool. Thanks.
Last question.
Maybe a simple question. I was curious that when you decide on the size of the subset that you choose, and if you go back to the plot, is there a correlation between?
Is it on the mic actually?
Yes.
Sorry, this plot or another one?
No, the previous plot.
Previous?
The plot. Yes.
This one? Yeah.
So now, on really the one where you show that the random performs quite well. So do you think is there a correlation between the size of the subset you choose and the performance of the random bits, or?
For sure, yes. So for sure, because full fine-tuning here would perform worse, actually, in comparison, right? So if you make this random subset too large, it also won't work that well. If you make it too small, then you don't have a lot of adaptivity. So you do need to find a sweet spot there. In this case, it was just around, we were operating on a subset of parameters in general that would, work relatively well in this context. So that's why you see that random weights are, are still working relatively well.
So currently there is no such matrix to decide on the specific size of the subset that you choose.
Yeah, not really, I would say. You can do something like, you can choose a quantile or, or a threshold directly if you want. So you could, so we have something, I mean, we were kind of thinking about it, but honestly didn't make it till the deadline to find something really satisfactory. But so the problem with that is that that it's kind of, in the end, it's likely also task specific. So we were looking in the question, like when you look at this one, if you could estimate something like the degree of hyperbolicness in some sense, right? Actually parabolic. And this, hyperbolicness actually. So, you could the degree of, sorry. So you can have the degree of, how strong basically do you have this kind of cross form. And we wanted to measure exactly that and then define that kind of threshold based on the shape of that kind of correlation, if you want so. It's just I'm not super happy with the result yet, but we are, but it's a great question.
Thanks. All right. So yeah, let's thank the speaker.
Thank you.
Thank you for inviting me, and thanks for the nice introduction. So I'm going to talk about dynamic sparsity in machine learning. Okay, so the work that I'm going to present has been done by this amazing team. So this is a recent photo that we took in one of our retreats. The group is called Sardine, as MT was saying, and you can see that you had to carefully pick the letters to get sardine in the end. For those who don't know, sardine is a very popular fish in Lisbon, and actually now we are in the season of the sardines. So the last activity that we did together was to go and eat sardines in Lisbon. Okay, so today I'm going to split this talk into 3 parts. I'm going to spend the most time in the first part, covering dynamic sparsity. This is based in a recent tutorial that we presented at the RIPS. And it's giving an overview of a line of research that we have been pursuing for some time. And then there's going to be like 2 shorter parts where I'm going to cover some of our recent works. One applying sparse transformations to conformal prediction, and another one that connects with the topic of this workshop, functional and relational learning. I might need to be selective in the interest of time. Yeah, so if you let me know when I'm about 15 minutes to the end, it will be good. Okay, so let's get started. So this tutorial that I was mentioning, it was I did it together with Eduardo Ponti. I think some of you might know him. I think he collaborates with some people here. The focus of the tutorial was on dynamic sparsity in machine learning. I'm just going to present some parts of the tutorial because the full tutorial is 2 hours. But if you're interested in the tutorial, feel free to get to that link or to scan the QR codes, and it will take you to the websites where you can see the slides and other materials. Let me just start by defining what is dynamic sparsity. And I realized from the previous talk that sparsity can be done in many different ways. So our focus here is going to be not so much sparsity in the parameter space as in the previous talk, but more sparsity in the activations. Okay, and that by dynamic I mean sparsity that is input dependent. As you provide a different input to the network, you are going to get like a different units that are going to get activated based on that inputs. But we are still flexible about what we mean by dynamic sparsity. There's lots of work that uses these ideas mostly with neural networks. There's the usefulness of these sparse activations is that they can induce neural pathways. If you think about things like sparse attention or values or sparse mixture of expert models, they're able to select circuits in your network that are going to be relevant given some inputs. But I'll also make the point that some of these ideas are actually inspired by more traditional work, like L1 regularization, sparse modeling techniques that bear some similarities with what we are doing here. So I should contrast these with static sparsity, which includes things like model pruning or sparse attention with fixed masks or fixed routing. So in our case, we really want the sparsity to be induced depending on the inputs. Why do you care about this? It can be useful for several different things. I will try to make the point that we can try to get better computational efficiency by being sparse, because there's going to be like a smaller subset of your network that is going to be used to make predictions. But we can also get some benefits in terms of interpretability. I'm not going to talk a lot about interpretability today. We can also induce better function specialization. This is what happens, for example, in sparse MOEs, or compositional generalization, or when we are handling long context information. Sparsity can also select what are the parts of the context that are relevant for the predictions that you want to make. So I'm going to cover a set of transformations that are able to induce sparsity and structure. They all have in common the property that they are differentiable, so we can do forward and backward propagation without any problem. We can use these sparse transformations both as hidden units in your network, for example, if you are doing attention mechanisms, or you can also plug them in output layers. And I'm going to talk a little bit in the second part, I'm going to talk a little bit about loss functions that are able to accommodate these sparse transformations. So I will use this notation throughout. So this is just notation for the probability simplex. I'm denoting by using this triangle here the set of vectors that are non-negative and sum to 1. So you can see them as probability vectors. Once in a while, I will abuse notation a little bit, and I will still use this triangle to denote measures in continuous spaces, probability measures or densities in continuous domains. But for now, let's just assume that everything is finite for the sake of simplicity. Okay, so in the tutorial, we covered like different kinds of transformations, starting from sparse transformations where we want to map from a set of scores or logits. You can think of them as logits if you want, unconstrained vectors. I'm using Z to when I want to talk about them. And what we want to do is to map these vectors to the probability simplex, right? But we want this transformation to be sparse. We want the probability distribution, the probability vector to have lots of zeros, because in many situations this is convenient. So I'll very briefly, I will talk a little bit about extending that to structured domains, where we have some marginal polytope that is associated with some graphical model or some structure problem, and we want sparsity in that structure set. I will talk about extending this to continuous domains, and I don't have time to cover the stochastic parts, but if you are interested in that, we presented that in the tutorial. Okay, so let's start with sparse transformations. Maybe the most famous example of a sparse activation is the ReLU. The definition is very simple. You take your Z, as in the previous picture, and you just return the positive part of Z. Okay, so all the entries of Z that are negative are going to be truncated to 0. The ones that are positive, they are propagated. So it's interesting to think about ReLU in this variational form. And this is going to become a little bit more relevant in a few slides. You can regard ReLU as this optimization problem, where given your input Z, you are going to return Y that minimizes the Euclidean distance to Z, subject to these non-negativity constraints. Okay, so in other words, you are projecting Z to the non-negative orthons. Okay, so this is going to be sparse in general. It's non-negative. It's one of the conditions that you want for probability vectors, but it's not going to be normalized, right? So it's not solving our problem if what we want in the end is to have a probability vector. We are lacking the normalization. So if you want normalization, then the most common transformation that we use is softmax, which I guess I don't need to explain to you because you probably saw it already many times. So softmax exponentiates each entry of Z and then normalizes. By construction, you get something that sums to 1. But it also has the property that it's strictly positive, right? So the probability entries can be arbitrarily small if we make the logits have a large magnitude, either positive or negative. If they are very negative, you are going to have very small entries for your probabilities, but they are never going to be exactly 0. And this is not just a detail. I'm going to argue that it's actually a strong limitation. And the reason for that is that the exponential function is strictly positive, right? It's never going to return zeros. In the other side of the spectrum, you have argmax, which is extremely sparse. It's as sparse as what you can get. Given the same z, it returns a one-hot vector that points to the largest entry of z. Okay, so you can see argmax from two angles that are equivalent. You can think of argmax as the solution of this problem, where we want to find the probability vector that maximizes the dot product with z. Okay, and the solution of this problem is to put all the probability mass in the largest entry of z. So we are going to get a one-hot vector as the result. Or we can also see it as a zero temperature limit of softmax, where we divide z by a temperature parameter called tau here. And when we make tau going to 0, we are going to get more and more peak distributions, and in the limit case, we are going to get a one-hot distribution. Okay, so I'm ignoring here the case where you have ties in z's. It's not very important, but these two things are essentially the same. Okay, so in this case, we have something that is sparse, but it's not very useful because if you have an argmax in a neural network, we cannot backpropagate gradients. We can, but the gradients are 0, right? So you are not going to be able to learn anything directly with argmax if you use gradient backpropagation. So on the other hand, we can take softmax, we can lower the temperature to make it closer to being sparse, but this is always going to be just an approximation to sparsity. And you might still have trouble with the gradients. You might still have vanishing gradients because gradients are going to decay exponentially fast as we decrease the temperature. So in fact, there is a nice paper by one of the speakers of this workshop, Razvan, where he points out some of the limitations of softmax, in particular regarding length generalization. So if you train a transformer model with sequences up to some length, and then we want to apply a test time on longer sequences, softmax fails even for very simple problems. So by softmax, I mean the softmax-based attention in transformers. Because of these dispersion effects where you start getting a lot of probability mass being wasted on tokens that are irrelevant. Okay, so let's get back to this thing, softmax and argmax. For a very simple example, if we have like a vector with 5 entries, a random vector of logits, softmax will give you something like this, where you can see that there are no zeros here, and argmax is going to put all the probability mass on the largest entry of z, which is the first one, but argmax is discontinuous, right? So if you perturb z a little bit, this bar is not going to move. If we perturb it a little bit more, then it might do a sudden jump to some other place, right? So you cannot hope to learn with gradient backpropagation. So what we would like to have is something like this, okay? Something that is sparse but differentiable. So if we have something like this, our hope is that as we slightly perturb z, a few bars are going to be affected, so we can still learn. There's going to be some gradients, but we are also ignoring a lot of labels that might be relevant. In this case, with 5 labels, maybe sparsity is not so important, but if you imagine a scenario where we have larger vectors, we might want to ignore some of these entries. So one possibility to do this is that is widely used is top K softmax, right? So the idea is very simple. We do softmax, we keep only the top K probabilities, and then we renormalize everything, right? So if we start with the previous example, we identify these 2 top probabilities, we renormalize, and we get something sparse. Okay, so this kind of gives us what we want. It's very used, for example, in MOE, in sparse MOEs for routing. But I don't like it very much because it has some disadvantages that I don't like. Like, one is that you need to fix K. The second one is that if you look at the landscape of this transformation, this is for a 3D example with K equals to 2, you have these discontinuities, right? You can see that there is this big vertical cliff that might cause some problems when you are learning with this kind of transformations. Fortunately, there are other possibilities for sparse transformation. So I'm going to talk a little bit about sparse-max, which I prefer to top K softmax, which is a transformation that basically takes our z and computes the Euclidean projection onto the simplex. Okay, so in other words, it's defined as the solution to this problem, where we are looking for the probability vector P that is the closest to Z in Euclidean distance, while being constrained to be in the simplex. Okay, so very simple definition. Another way of writing the same thing is if you expand this square and we ignore constant terms, you can also see as the solution of this problem, where we have this part in black here, which is exactly what we had before in the definition of argmax, right? If you just had this part in black, the solution will be a one-hot vector, indicating the largest entry of Z, but we have this L2 regularization term that is trying to push for probability distributions that are a little bit more uniform, right? But the good thing about these Euclidean projections is that they can hit the boundary of the simplex, right? So if you want to imagine that suppose that I'm holding a simplex here and there is a point somewhere there, as you move this point further and further away and you project onto the simplex, chances are higher that you're going to hit a corner of the simplex or a boundary point of the simplex. And the boundary points of the simplex correspond precisely to the probability distributions that are sparse. Okay, so this is what gives the name Sparsmax. So this transformation is end-to-end differentiable, and in fact we can do the computations efficiently. The forward pass can, a naive algorithm takes k log k time. It can also be done in linear time. It's a little bit slower than softmax, but not too much slower. And the backprop can actually be faster because the gradients are sparse. Okay, and I'm going to talk a little bit about recent implementations that we have, like a flash attention version for this kind of transformations that are quite fast. Okay, so basically with Sparsmax you have something like this as we wanted, and another interesting angle to refer to Sparsmax that now makes you understand why I introduced value in this variational form is that we can see Sparsmax as a normalized value, right? If we take the value in the variational form that I have written earlier, and you just add the constraints, the normalization constraints, then what we have is exactly Sparsmax, right? This is the same thing. These two constraints are the same thing as saying that Y is in the simplex, okay? So you can regard Sparsmax as a normalized version of value. So how does it look geometrically? So, in 2D, softmax looks like this. And Sparsmax is a piecewise linear function that has similar asymptotics, but it has these exact saturation patterns. This is what gives us the sparsity. If you look at larger dimensions, it's similar, right? So Sparsmax is always a piecewise linear function. The asymptotics are very similar to the ones that we have with softmax. In the middle, I'm plotting top case softmax. You can see that softmax doesn't have these vertical cliffs, right? So it doesn't have this issue that I pointed out with top case softmax. Okay, so, but of course there's other sparse transformations that you might want to use. Sparsmax is not the only one. And there is a very nice paper by Vlad Nicolai and Mathieu Blondel, shortly after we proposed Sparsmax, which looks at this from a more general angle, assuming that we have some convex function omega, and we use omega to regularize the problem that corresponds to argmax. Okay, so they call this the omega regularized argmax transformation. So, if we don't use any regularization, we just have the part in black, and this corresponds to argmax, as I showed in the beginning. If we use L2 regularization, then we have Sparsmax. And it turns out that if you choose the negative Shannon entropy for omega, then we get softmax. Okay, so those of you who are familiar with convex duality and convex analysis know that there is this relationship between Shannon entropy and the log partition function and softmax. Okay, in general, we can think of this omega as something that is a generalized entropy, right? So if you generalize Shannon entropy to something that still has the same properties that we want for an entropy function, or a negative entropy function, then we can obtain transformations that can be insightful. And I'm going to show some examples of that. Okay, so the example that I'm going to focus more on this talk, we cover others in the tutorial, is Antmax, which is based on Tsallis entropy. How many of you know what Tsallis entropy is? Okay, a few. So I really like this entropy, and I was very fortunate to have Tsallis visiting our lab 2 or 3 years ago, where we had some nice conversations about this. So the Thales entropy has been proposed in the context of physics, to solve several problems in physics for which it will be interesting to consider entropy generalizations. And this is the definition of the Thales negentropy. Okay, so it's parameterized by a parameter alpha, which is greater than or equal to 0. When alpha is 1, we recover Shannon entropy. When alpha is different from 1, we use this expression, which in the limit, if you make alpha tend to 1, you're going to get an indetermination. If you solve the indetermination, you get the expression in the second part. Okay, so this is a continuous parametric family that includes Shannon entropy as a particular case. And for several reasons, you can think of this as something that has the same flavor as an entropy. I forgot to mention one thing. So the reason I'm using this notation here is that, again, this comes from Untitled Duality, right? So when you pick, when we have this expression, this corresponds to the gradient mapping of the conjugates of omega, right? So if we use this entropy and you consider this generalized argmax, then you're going to recover the 3 cases that I pointed out before for specific values of alpha. Okay, so when alpha is 1, we get this expression, so we get softmax. When alpha is 2, we are going to get L2 regularization plus some constant term. So this is equivalent to sparse-max. When we make alpha go to infinity, we are going to get argmax. Now, this is interesting because for any alpha that is greater than 1, strictly greater than 1, we are always going to get the possibility of getting a sparse probability distribution. So we just need to move a little bit beyond softmax to have this possibility of getting a sparse probability. And the sparsity is going to increase with alpha. Okay, we should not regard this alpha as a temperature. It's something a little bit different, but it also has the property that as you increase alpha for the same z, for the same logits, the sparsity is going to increase. And there are efficient algorithms that can be used to do forward and backward propagation with this alpha and max family. Okay. So in 2D kind of looks like this. You can see that we can interpolate between softmax and argmax. We have this package if you want to play with this. You just need to pip install entmax, and every time in your code where you're using softmax, you can experiment with entmax and play with alpha. We have some Jupyter notebooks in the webpage of our tutorial where we can play with this. So yeah, here I'm just adding 1.5, which is one example of alpha that works very well for many different applications where we tried. Which you can see it's still sparse, not as sparse as sparse-max, but you still have a 0 for this example. Okay. Okay, so where can we use this? So the first place where we thought about using this was in attention, in the context of machine translation. So how many of you are familiar with machine translation? Okay, a few, more than what I expected. So in neural machine translation, there was this idea of taking inspiration by the IBM models that model these word alignments. So aligning words in the source with words in the targets by doing something with soft alignments, by using softmax-based attention, right? So our motivation was, okay, let's remove softmax, let's replace it by entmax, and try to get some sparse alignments that are a little bit closer to the ones that came from statistical machine translation time, before neural networks. We can argue that you can have a little bit better interpretability by doing that. We did some works where we also learn alpha, so you can also backpropagate through alpha. And if you are working with transformers that have many attention heads, there might be good reasons why some attention heads tend to be more sparse and others less sparse. So you might want to attach a specific alpha to each attention head. And we do some analysis in this paper. And we can also, use the same thing for, in different problems in expandable AI. Okay. So recently, this was this week actually, we just put out this paper in arXiv where we studied the lens generalization properties of these sparse transformations, and we see both theoretically and empirically that entmax suffers less from dispersion, representational collapse, and some issues that have been observed with softmax, which we find very exciting. So take a look at the paper if you are interested in this topic. Another thing that is very recent, it's going to be an oral paper at ICML, was AdaSplash. This is an efficient implementation of Nmax that is particularly convenient if you are playing with long contexts. Okay, so you can see that if you are sufficiently sparse, then AdaSplash can, with our Triton implementation, for those who don't know, Triton is like something in between CUDA and PyTorch. That gives you some flexibility about how to work with the fast memory of your GPU. So AdaSplash, is faster than super optimized flash attention 2 if we are sparse enough. Okay, so the reason for that is that you can throw away a lot of blocks that are just containing zeros, and this is something that we are also very excited about. Not only it's faster, but actually by replacing several models, if you replace attention heads with the alpha Nmax, you can also observe better performance in several tasks. So these are some experiments that we did with Roberta and modern BERT. We should try with NeoBERT as well, and other BERT models that have been released. Okay, so this finishes the first part with sparse transformations. I can take questions now if there are any questions, otherwise I will just proceed. Okay, so I'll just proceed.
But maybe I wanted to ask one thing, sorry. Okay, too late, I'm asking. The slide that you showed where you have the entropy and then alpha, right? I always wondered for many, many years, I think maybe it's the previous one, yeah. Because this is like, for me, always like conjugate Bayesian inference. And then none of the paper ever talked about this. And if I talk to Matthew, it doesn't even kind of, doesn't even think that it's important. So I wonder what happens. Like, I guess you know this, right?
You said conjugate Bayesian?
Yeah, like conjugate Bayes is essentially this operation with omega being the KL, the Shannon entropy.
Oh, okay, right.
And then the linear term is always, whenever you take a conjugate Bayesian model, the linear term always exists. Like Z is like, in this case, would be T of theta in our notation. It's always linear.
Yeah. This is very prevalent in a lot of scenarios, including that one. I'm going to talk a little bit more about that in the end of the talk, when I talk about facial and rational inference, where we are using these kind of constructions in a setting similar to the Bayesian learning rule that you presented before. So I will come back to that. Okay, there's more questions.
So, like since softmax is used like in a lot of things, like in machine learning, so builds like, what's the kind of trade-off when you're using, for example, Nmax to softmax? Is there like kind of like a trade-off, or is it like?
What do you mean by trade-off? In speed, accuracy?
You lose something.
Yeah, what do you like, what's the kind you gain out of things by using Nmax?
I think you don't lose much. I mean, it's a little bit slower. Unless you have enough sparsity, as I was pointing out with this new flash attention implementation. So you kind of might lose speed, but again flexibility, because the family of alpha Nmax includes softmax as a particular case, right? So in the worst case, alpha can be close to 1. And you tend to, so I don't have that in the slides, but something that is interesting to think about is language models trained with softmax, when they generate, most of the time you do some truncation at test time. You do top K or nucleus sampling, something like that. But if you instead use these kind of sparse transformations, you don't need to do this truncation at test time. You already learn the model to predict something that is sparse. So I think this is actually a very natural choice that you can make. So I don't think there is necessarily a trade-off except for efficiency.
I guess so. It depends on the sparsity, but since it comes naturally in a lot of problems, then it's really very good, and you can also do it.
Yeah.
No, thank you.
Actually, I have a follow-up question on this, because I'm also wondering about the learning dynamics of alpha. Did you see something like, could there be a benefit, for instance, to anneal alpha, for instance, towards something that's sparser? Do you see potentially, I'm just thinking about this, a similar because we saw in dynamic sparse training or in general sparsification that it's good for some time to train with something that's less sparse but becomes sparser later. Also,
yeah.
You see similar effects?
Excellent question. So so I don't have that in the slides, but in this paper we studied the dynamics of a learning alpha, and we see that things differ depending on which attention heads you are looking at. In some cases, so the attention heads they tend to start dense. Or more dense, and then some of them just prefer to keep being dense. Others, they start becoming more sparse. So you have like these two different behaviors that we observe. But yeah, this is regarding the annealing part. We use it when we start from a pre-trained model with softmax. If you just replace it instantaneously by, let's say, 1.5 endmax, it doesn't work well. So, but if you anneal alpha, then the model adapts to that choice, which is convenient because you don't want to train from scratch a very large LLM replacing softmax by endmax, but you can take an existing checkpoint and adapt. That's what we did in these experiments. We started with the models that were using softmax, and then we did annealing to adapt to different alphas.
Do you train them on the same data, or do you train on your fine-tuning data, or do you maybe even have a student-teacher setup and where you use
on the same data?
Have a similar function as before, but sparse representation.
No, this was in the same data. So we adapted, if I recall correctly, we adapted Roberta and modern birds. Roberta and modern birds for different values of alpha on the same data. But in all cases, starting from the model that was trained with softmax.
Thank you.
You pick alpha too large. Do you observe like dead neurons, like for Redu, something
okay.
neuron which cannot become alive again? So maybe
that's a good question.
4 or 5. Then
so I guess it depends on the. I mean, of course, if you have there's going to be some value of alpha that is too large where that is going to happen because in the limits it becomes argmax, so you're going to have vanishing gradients. In practice, we don't usually make alpha super large, but in our experiments with in these lens generalization experiments, we actually managed to use quite large values of alpha for simple tasks, and the model still learned, which was interesting. But yeah, of course, there is a limit. Like if you make it too large, there's going to be problems. For a range between 1 and 2, we never saw any issues. Okay, so I'm going to continue. So these ideas can be extended to the structured case. Okay, so I'm just going to give you the basic flavor because I don't have time to cover everything. But so something that we did try was to include constraints on top of this optimization problem that I was showing. For example, in some problems, you might want to bound the amount of attention that a word can receive. For example, in machine translation, there is this concept of fertility, which is related to how many words in a target the source word can be aligned to, and we can control repetitions by trying to push the model to a word not receiving too much attention. Okay, and this is possible by building something called constraint sparse-max or constraint softmax, or constraint endmax, where we include these extra constraints. It's also possible in some problems. It makes sense to try to encourage attention to be in contiguous tokens, or if you are working with images on contiguous regions. For example, if you want to attend to regions of the image that are compact. And you can also extend these ideas with the fused max or TV max for the case of images, where we tend to get attention maps that are more compact, as shown in this plot. Okay, so in both cases, we take advantage of the structure of the problem. Another way of using structure is sparse map. This is work by Vlad Nikolai, where we basically generalize these ideas to structured problems. If you have a graphical model or a structured problem for which that you can represent as a marginal polytope. Are you familiar with marginal polytopes? Okay, well, if you are not, don't worry. This is not going to be very important for the rest of the talk. You can see this as a generalization of the simplex, but in a way that encodes the structure of your problem. And the vertices of the marginal polytope correspond to the structures that you want to decode. Okay, so if you do map inference, you are going to return a vertex. If you do marginal inference, for example, with some product belief propagation or something like that, then you are going to get a point inside the polytope. If you use sparse map, you are doing an Euclidean projection onto the polytope, and you're going to return a sparse combination of structures. And this can be interesting for many different things. Okay, and in fact, we have efficient algorithms for computing these projections, even for problems that can be very complicated. So an extension of this idea is LP sparse map, where we can actually combine multiple structure problems and solve arbitrary problems in a factor graph. And we actually applied this to several different problems in explainability, in structured upfield networks. I don't have time to cover all that, but I'm just showing this example for upfield networks or associative memories. How many of you are familiar with associative memories, upfield networks? Okay. They became more popular now because of the Nobel Prize that was given to John Upfield. In fact, I think Amari and Nakano should also have received that Nobel Prize because they did a lot of relevant work before Upfield in associative memories. So our idea here is, that there's a lot of recent work on this on Upfield networks that tries to replace the traditional energy functions by something continuous. And what you get is these attractors that correspond to the patterns that are memorized, but the attractors are only approximating those points. But if you use these sparse transformations, you can actually get exact retrieval, just as in traditional upfield networks. And you can still have a very large memory capacity, as in these recent extensions. So this kind of gets the best of both worlds. And you can also encode structure if you want to return not just a pattern, but some association between multiple patterns. Okay, so I know this was a very summarized description, but if you are curious, you can talk about this in the end, or you can just check what we have in this paper and in the tutorial. Okay, so I will hand this part by talking about continuous attention, which is something that I'm very excited about. So most of the time when people talk about attention mechanisms, they think about attending to finite sets, right? For example, a sequence of tokens or regions in an image and so on. But in fact, the same idea can be generalized to arbitrary domains, right? If you have a measurable space where you can define probability densities, you can also have an attention that is a probability density as opposed to a probability mass function. I would argue that in many problems, it kind of makes sense to work on these continuous domains. For example, if you are looking at modalities like speech or video or any continuous time signals, you might want to have some parametric representation of this continuous signal as opposed to just representing everything as a sequence of tokens. And in fact, we played a little bit with those things. I'm going to mention one application. So just to explain this picture, in the classical setting, you have like some z, some discrete points. And then the attention probabilities correspond to some probability mass function. And when we multiply the probabilities by the values, your values are going to look like these, and you are computing like an average of these columns. Okay. When you move to a continuous domain, we start with a signal that is continuous. We have a probability density function as opposed to a probability mass function, and your values are also a value function, also a parametric function in a continuous domain. But the main ingredients are the same. Okay. So we applied this to video recently. This is another paper at ICML, where current models, they process videos by chunks, and then they keep like local memory for each chunk, but they have trouble retaining global memory about the entire video sequence. This is why models degrade if you try to make them, if we try to use them for long videos. So what we do is we use a global memory that is a continuous time parametric model that uses this continuous attention to enrich existing video models without any training. So this approach is very simple. It's a training-free approach. You take a pre-trained model, we add this continuous time parametric global memory on top, and it works. And this framework can process videos of any length. Okay, so it never drops any tokens because we are working on a continuous domain. Instead, what we do is we compress segments of the video that are less relevant, and you give more prominence to parts of the video that are important, that you want to keep in memory. So just to give you an idea about how this is done, we need to have some sort of memory consolidation process. Every time new information comes in, we have like a sequence of discrete points because the local memory is still discrete. And we need to merge it with our long-term memory representation, which is continuous. And we do that by sampling points from this long-term memory, concatenating with the new information, and then doing regression to obtain something continuous again. Okay, this is the process by which we update the memory. And the way which we do the sampling, we can use to control how much granularity you want to have in specific parts of the memory. So maybe some segments of the video are more important, you want to sample more there, and other parts are less relevant and you want to sample less there. Okay, and by doing
what is memory here?
Oh,
to understand.
So memory here is basically everything that. So you imagine that you are processing a video in one go, okay? And we don't want to use, to represent everything in brute force. You don't want to remember every pixel of the video, right? It's too much information. You want to have, you want to keep in memory the parts of the video that are relevant for you, for example, to answer questions about the video in the end.
So it's some kind of like smoothing of things to compress stuff.
Yeah, what we do is we build like a compressed version of the video, but the compression is built on the fly as you process the video. That's what I'm calling a long-term memory.
I see. So this is just for like any signal that comes in, you can just represent it by doing some window stuff that you're running. Okay.
And the compression is enabled because since we are working on a continuous space, this is a parametric model. You need to choose a number of basis functions. Okay. But the number of basis functions that you choose can be much less than the number of tokens that you would choose if you represent everything as a sequence of tokens. That's the basic idea.
Yeah.
So this is for video, but it works with other kinds of data, of course. So this memory consolidation process allows you to form sticky memories. These are regions of the memory that are stickier, that you want to have more resolution about. And we play a little bit with that, with movie data. Okay, so here's the summary so far. How much time do I have for the rest?
So you have exactly 15 minutes from now.
15, okay.
Like to the end of the talk.
Okay, yes. Including the questions. Yes. Okay, so I need to, okay.
I have a question.
Yeah.
So your sticky memory or some representative frames are maybe similar to keyframes, the notion of keyframes in the video. Do you have any comparison between this representative frames and the keyframes?
Yeah, so we can regard the sticky memories as keyframes with the difference that it's not necessarily just a single frame, because you are not just storing single frames. You are storing representations that can be multiple frames more or less around the same time. In the paper, we compare with different approaches. I don't know if we compare specifically to something that uses keyframes, but we compare with other models that have different ways of organizing the memory. Okay, so this is the summary so far. Okay, so I covered all these different transformations. They're all differentiable. They can work in discrete domains and in continuous domains. I didn't cover the stochastic parts, but happy to talk about that some other time. We can use these as hidden layers or as output layers, and there's plenty of applications. Okay, so now I will talk about how can we deal with sparsity in the output space. Right. So far I talked about sparsity mostly with attention, and in fact, entmax can also be used as a loss in the output layer, something that replaces cross entropy loss, for example. But there, it's not straightforward to do that. If you still maximize log probability, because now the probability can be 0, you run the risk of getting logs of zeros, right? You can screw up your objective function if we insist in using log likelihoods. So what we propose instead is to use a different class of loss functions called Fenchel losses, which I'm going to cover now, which are a natural solution to this problem, and they can accommodate sparsity without any issue. Okay, and there's several applications. I might not have time to cover the conformal prediction one, unless people are specifically excited about it. You don't? Okay. It's not Bayesian enough. So I will just provide the main idea of conformal prediction, and then I will try to spend a little bit more time on Fenchelian relational inference. But before that, I'm going to go back to the optimization problem that you mentioned. So, right, this is how we define the omega regularized argmax. You have this connection with the gradient mapping of the conjugates of omega. And we saw before that these transformations, we can use any omega we like that can be seen as a generalized negative entropy. Now we're going to develop a loss function that also builds on top of this construction. Okay. So let's suppose that you have some scores. Okay. For example, logits in your output layer, and there is some ground truth, which can be a one-hot vector, but it can also be a probability vector for your labels. Okay. For example, if you're doing distillation, you want to have this to be a probability distribution and not just a one-hot vector. Okay. And we want to have a loss function that measures how consistent are your scores with this ground truth. Okay, and we can build one by considering the convex conjugates of our omega. So if omega was Shannon entropy, this convex conjugate will be the log partition function. Okay, and we can form a loss function that looks like this. Okay. So it's the sum of the conjugate plus omega minus this linear term. Okay. For those of you that are familiar with convex analysis, you might have recognized this as the left-hand side of the Fenchel-Young inequality. So the Fenchel-Young inequality states that this is always greater than or equal to 0, which is a property that we want loss functions to have, right? So this loss function automatically gets this property from the Fenchel-Young inequality, right? This is what gives the name Fenchel-Young losses. On top of that, it's 0 if and only if Q and Z are perfectly calibrated, meaning that the gradient mapping, so let's say Ntmax, the Ntmax transformation of Z gives Q, okay? This means that our logits are going to give exactly the ground truth. You should get a 0 loss in that case, and you get that with this logic. And there's also a few other nice properties. For example, this function is convex on Z, it's differentiable, and the gradient of this loss takes this form, where this part here is the omega regularized argmax, let's say Ntmax, and this part here is the ground truth. Okay, so it's very straightforward. If you have an algorithm that computes your sparse transformation, you can use it to compute the gradient of this loss. And so this recovers cross entropy loss. Again, when we use Shannon entropy as omega, it recovers other losses that are using machine learning. This is also heavily related to Bregman divergences. In fact, Amani calls these mixed type Bregman divergences. Mixed type because in Bregman divergences, you typically use them to compare a divergence between two objects of the same kind. For example, two probability distributions. Here, what we are doing is we have probability distributions in one side and its duals, which are, let's say, logits on the other side, right? So, but the two things are not exactly equivalent, but very similar. And we, in this paper, we describe exactly what the relation is. Okay, so yeah, so the interesting thing about these Fenchel-Young losses is that if you remember support vector machines, some of you might still be from that time, you might remember that SVMs have margins, right? The hinge loss gives you a margin. It turns out that if you have sparse transformations, of which Ntmax are an example, you are also going to have a margin when you use Fenchel-Young losses, which I find pretty neat, okay? So margins and sparsity are concepts that are related to each other. And in fact, we can even quantify the size of the margin in the Ntmax family, okay? So this entire thing, I'm talking just about the discrete case where P is a vector, but this entire thing can also be extended to include continuous domains. We have a JMLR paper that provides all the details about that. But now I'm going to maybe just how much time do I still have? 5 minutes?
We have about 8 minutes, I think.
Okay, so maybe I will just summarize this in one. How many of you are familiar with conformal prediction? Okay. So I'm just going to provide the main idea. I don't have time to define conformal prediction, so I think I will ruin the 8 minutes if I would do that. If you're not familiar with conformal prediction, you might not get the point. But so conformal prediction is a method that or a family of methods that is used for uncertainty quantification that comes with certain guarantees. Okay, so you, instead of building a point prediction, you have a prediction set, and you have certain guarantees that with some specified probability, your true class is in that prediction set. Okay, so people like it because it comes with these theoretical guarantees. Now, there's tons of other uncertainty quantification methods. For example, temperature scaling is a very common one, which is kind of more an heuristic, right? You train your models with, let's say, softmax, with cross entropy loss, and then you tune the temperature on your, you take your pre-trained model, you change the temperature parameter so that the model becomes better calibrated. And you can also try to get some uncertainty quantification from there. But these are two different sets of methods. So what happens, and this is what we show in this paper at AI Stats that we recently published in AI Stats, what we show is that the two can meet if we consider these sparse transformations. Okay, so in fact, the fact that transformations like sparse-max or ant-max give you a sparse probability vector makes you able to interpret the things that are non-zeros as the elements of your prediction set, right? And now the question is, what should be the temperature that you want to choose so that you get exactly the prediction set of the size that you want with the guarantees that you want to have about including the correct label. So these plots are showing for different values of alpha the regularization path as you change the temperature, which is the x-axis, how your probabilities are going to look like. And while in softmax you can only it's always dense, right? If we use alpha ant-max with alpha greater than 1, there is a point where we are starting to remove some labels from your prediction sets, right? So if you choose the right temperature, you have like a specific prediction sets that you are building. So that's the idea. And then what we do is try to understand what non-conformity score, which is the quantity that is important in the conformal prediction, does this correspond to? And you find that there is a very natural choice of non-conformity score that corresponds to this technique. Okay, so I'm not going to get into details, but yeah. So if we have time in the end, I can go back to this topic. Okay. Okay, and this works empirically and so on. So okay, I'm going to move on to the last thing, which I confess it was very rushed. So it's hopefully like a basis for a conversation, but it's still, we are still doing some work on top of this. This is work being done by Sophia, who is going to be an intern here in this group soon, hopefully, and some of my students and my colleague Mario Figueiredo. So I will start from Bayes rule, okay, which I think is suitable for this workshop. I don't need to explain you what Bayes rule is. But I want to make this connection with the variational form of Bayes rule that has been rediscovered several times. This reference Zellner gives a lot of details about this. So you can interpret Bayes rule in this form. You can see it as the posterior being the argmin, where your variable is can be seen as a variational distribution. Let's call it Q. Of the sum of two terms. One is an expected conditional likelihood, where the expectation is with respect to this Q. And the second term is the KL divergence between Q and the prior. So basically, you don't want to deviate too much from the prior, but you want to choose your Q to minimize as much as you can this expected log likelihood. So there is this trade-off between these two terms. This entire thing, for any choice of Q, in physics, it's called the Fourier energy, right? Or the variational Fourier energy in this context. And so your goal is to choose the Q that minimizes the free energy, okay? And this Q is going to coincide exactly with your posterior, okay? So not only that, but if you take the mean instead of the argmin, what you're going to get is the evidence, or minus log of the evidence, okay? So of course, if in some problems you cannot do this optimization directly in the manifold where Q lives, which might not be the simplex, might be a complicated continuous domain, but you might have some statistical family that is tractable. Okay, so what is commonly done is to replace this, the original space of probabilities by a family Q, calligraphic Q, and then what you have is going to be evidence lower bounds, or DL, Okay, so you are going to obtain by minimizing this free energy something that is a lower bound to the evidence or an upper bound to minus the evidence. And you only get an approximation in your posterior. Okay, I guess this is something that most of you are already familiar with. Okay, so of course there are ways to generalize this idea, and some of them came from this group. We could replace the likelihood by an arbitrary loss function, pick your favorites, and build something that we can see as a pseudo posterior, if you want. Okay. In fact, you can recover many well-known machine learning objectives. The learning rule paper shows that if you use an algorithm based on natural gradients to optimize this, we can recover many interesting techniques. But it's also interesting to look at how we can replace the scale divergence by a different regularizer. At least this is something I'm interested in. Okay, and as you might imagine, what we're going to do is to replace it by a Fenchel loss. Okay, which is more general. I'm calling it a Fenchel regularizer because we are using it more as a regularizer and not as much as a loss. So what are we doing here? So we also have a loss as we had before. So the only thing that you are changing is the KL. You are going to use this term instead. If you prefer to think in terms of Bregman divergences, you might also think that this is a Bregman divergence between your prior and your variational distribution, or vice versa, your posterior distribution and your prior. But if you want to use sparsity, it makes more sense to use Fenchel losses. Okay, and here this eta here is like a log prior. You can think of it as parameters of your prior, not the prior distribution itself. And you want to penalize miscalibrations between this log prior and your variational distribution, and at the same time minimize the expected loss. So you can think of this eta. Okay, so let me explain these steps. So in the previous slide, I had this formula for the Fenchel loss, right? That was the sum of omega of q plus the omega conjugate of eta minus q transpose eta. So the omega star, it's a constant with respect to q, so you can take it out. The dot product, it's absorbed in this expectation, okay? So this line is exactly the same as this one. So you can also see it as an expectation of the loss minus eta plus the entropy regularization, the generalized entropy regularization. And now, written in this form, this kind of, I think, goes back to your question. You can interpret this as the gradient conjugate mapping, right? You have this direct expression that connects you from the log prior and the conditional, I'm putting quotes here, the log prior and the conditional log likelihood, which is your loss, to the pseudo posterior. Okay, so I would say that this is another way of expressing Bayes rule, right? That is more general than the original Bayes rule, right? That makes this bridge with convex duality. So I'm particularly interested in the case where omega is at Sally's negentropy, where you can get Nmax, you can get a sparse posterior when alpha is greater than 1. Of course, you can derive a lot of algorithms from these constructions. For example, you can have DM algorithm. In this case, what you want to do is to minimize free energy and learn the model at the same time. So this loss function is parameterized by some eta parameter. I guess I need to finish. Okay, so and you just alternate between this E step where we perform this mapping that I was mentioning before, and the M step corresponds to minimizing the expected loss. Okay, so we experimented with this for simple clustering problems and a few other problems, but I'm going to wrap up because we need to finish. So in this second part, I talked about Fenchel losses. These are a wide class of losses that generalizes cross entropy and others. They support sparse probabilities, which cross entropy doesn't. This idea of Fenchel variational inference can be seen as a generalization of Bayes rule. It's possible to generalize a few other concepts. I didn't talk about that, but I want to emphasize that we also had this additivity property that you mentioned yesterday or Monday in the canonical space. If you look at this expression, if this loss is a sum of losses, right, then you can also incrementally update, additively things in the canonical space. and then in the end project to your space. There is a catch here, which is you no longer factor the posterior as a product of terms unless you are working with the Shannon entropy. I don't know if this is a bug or feature. It's up for discussion. So another thing is when omega is a sparse-inducing entropy, this mapping might lose information due to the sparsity, right? So logics that if some logic is mapped to a zero probability, then you can no longer invert this mapping. You can no longer know what was the original loss. Yes. And this means that these Bayesian updates they have to be all performed in a canonical space before we project them to the mean space. So if every time a new data point comes in, you compute your posterior, then you might not be you might lose some information. Okay, that's it. Thank you.
It's a pleasure to be here today, to be part of this workshop, to be in Japan. I'm still a bit jet lagged, so apologies for if I'm struggling finding the right words. I woke up at 3 a.m. For some reason. It doesn't make sense in Japanese time. It doesn't make sense in German time. All right, so I'll talk about lessons from sampling Bayesian neural networks, which would actually be a very, I would say, easily digestible talk, rather on on the empirical side. So not super technical, which is maybe good after lunch. So this is joint work with many other collaborators. The key contributors are PhD students that I super or co-supervise. It was a tough decision to talk about this, or I could have also talked about sparsity neural networks, and then it would relate to the first two talks. But this is at least, well, not at least, but this is Bayesian. So this was the most Bayesian it can get. So I'll talk about sampling in Bayesian neural networks. And if you talk to people about this, the common perception is, first of all, why do you do this? You don't have meaningful priors in the weight space. It's too expensive. It's only for small scale. And it's impractical due to the symmetries. And in this talk, I want to challenge all of these aspects. I will do this by first giving a short introduction, which will actually be an unconventional introduction. It will show the results already. And then by this showing the results, I want to say that it can be quite successful to do sampling in Bayesian neural networks. And in my main part, we'll talk about the ingredients for the success, also related to overparameterization. So there's a bit of connection to the first talk, and also optimization. And then 3 is sort of the results section where I show some qualitative results. 4 and 5 are already wrapping things up, current bottlenecks, and summary. All right, so I start with the introduction. And before I go into the details, as I promised, here are already some numbers. You don't need to look at every number in particular. It's Laplace mean field variation inference, a deep ensemble with 10 members. Here in the different columns, the different rows are the four first rows are the log pointers predictive densities, and the second 4 rows are root mean squared errors. You can see here that for different data sets, different methods perform the best. Deep ensemble is often, in most cases, the best choice here. And now what you can do is, if you have your deep ensemble with your 10 members, you can use these as starting values for a sampling technique and start sampling from these 10 different, let's say modes for simplicity that you found with deep ensembles. And if you do that, you see that you get quite notably better in performance in both the LPVD and the RMSE. In the RMSE, we are able to reduce the error by almost 50% by adding sampling on top of the deep ensemble. And for the LPVD, you also see already on this, if you look at the signs of the numbers, that we are in a quite different ballpark. And you might now say that this is obvious because you're taking deep ensemble, which already maybe is something that performs well, and then you add sampling on top. This is obvious, You could also just look into. Okay, so the point here is that if you look into the blue numbers, they indicate that well, sampling itself, not with the deep ensemble approach upfront, but sampling itself already is better than the deep ensemble. If you do the Bayesian model averaging with sampling with just one chain and not 10 chains, that can be maybe even better characterize the posterior, better be perform better than a deep ensemble. You might still be a bit skeptical because sampling is usually, well, this was small scale. Here are some larger scale, not super large scale like we saw before, but MNIST, Fashion MNIST, IMDb. These are things that you can now easily also sample from in reasonable amount of time. You see again on the very right side is the Bayesian deep ensemble, which is essentially the thing that I said before. You take a deep ensemble and from the members you start sampling. So you take the deep ensemble members as initial values, as warm starts for the chains that you use them to sample from. And again, the Bayesian deep ensemble performs better than the deep ensemble. And also, if you look into the average chain of these sampling approaches, which is the column with the blue values, they perform better in most cases than the deep ensemble already. So there's something to sampling that drives this performance.
So if you sample, how many times?
Yeah, that I didn't say, and this also clearly makes a difference. Yeah, so the that depends. So I can maybe show later some results where you see that it depends on the task and the network how long you sample. Sometimes it only takes 10-ish, sometimes 100 samples, sometimes it takes even more than that.
So can you then also explain what the average chain is?
The average chain is, so you have 12, in this case you have 12 chains that you run from these 12 starting points, and then each of these chains has a different performance, in this case in LPPD, and then you can check what is the average performance of all of these chains, meaning it's not the best chain that we pick, not the worst chain that we pick, what would be an average chain that you get in sampling. And this is performing better than, well, not only the deep ensemble, but also, well, obviously than the average chain of the deep neural network.
One chain is one sample?
One chain is, no, so one chain is meaning you get X samples. I don't have the number for the X here. Well, I have, I think, but it's, it depends on the task and the network. Yeah. All right, so especially with that, maybe also related to your question, you might be skeptical about, well, then it gets more budget, right? If you sample 1,000 samples, that's maybe an unfair comparison. That's also something we have addressed in one of our papers recently. So we could, for example, look at these, the second last pairs of bar plots, the BDE1, which is essentially an optimization approach, and then followed by sampling. So this guy here. And then you can check what is its LPPD and try to find a matching LPPD of a deep ensemble, which is in this case a deep ensemble with 35 members. But then if you do that, you see that, well, the deep ensemble with 35 members has actually a longer runtimes than the sampling approach. So it's not that the sampling gets more time budget. And in this case, actually with matching performances is faster than a deep ensemble with 35 members. And this because the talk will be also mainly about scalability and efficiency. This is a point that I want to make here. Sampling is not something that necessarily takes forever or takes much longer than optimization. So here you have in the rows again different data sets. The columns are a deep ensemble, and then how much time does it take to add sampling on top using either the NUTS sampler or our sampler, which I'll explain later. And you see that, for example, for the protein data set, fair enough, if you would, or you do deep ensemble, it takes 12 minutes. And then if you would add NUTS sampling on top, it takes 2.5 hours. This is, I see the point if people say this is too expensive, it takes too long. But then if you use our approach, you only sample, you get, it takes only 19 minutes. So it's roughly the same ballpark as the optimization. Same for, I don't know, the bike sharing data set. It takes 5 minutes for optimization. It takes 5 minutes for sampling. So we're in the same ballpark. Yeah.
Sorry, can you explain that for someone who's not very familiar with the details of Bayesian neural networks? So you still optimize, right? Also in your approach. And on top, you do also do some sampling, and this doesn't take long. Is that the argument, or do you do something else in optimization there?
No. So a good question. So in this case, the plus means this is the additional time. Well, so we have 2 times the run. Like if you take both together, if you use a deep ensemble, and on top of this you do the sampling, then it will take 10 minutes in the case of the B data set, bike sharing data set. So it takes longer because you do once the optimization first and then you do sampling. This combined approach is not something that people would naturally do in sampling. They would start without the optimization first, but this is something that I will explain later is essential for sampling from Bayesian neural networks. But yeah, this is the additional time it then takes for sampling. To answer your question, yeah.
So I think I would also like to understand what you're sampling, kind of, and so where you know what to sample from, or what you sample also, because somehow you will have parameters, right? But sorry, maybe you can also just continue with your talk and I'll figure it out.
No, I mean, mic is right there. I think it's just the Zoom, people cannot hear you.
Okay, good, sorry. I was just more wondering, much more basic kind of, what exactly you're sampling there. So how do you get the parameters of the Bayesian neural network from which you want to sample, for instance?
Good question. I think, so you, and in the cases that I show, I can also maybe go to the, because I wanted to talk about the ingredients for the success. I wanted to talk about the setup anyway. So what we do is you take a neural network and you define all of these weights to be now random variables with a distribution. You assume a prior, and that's something I'll have on the slide. You have a prior in the weight space. So you take, for example, a standard Gaussian, independent standard Gaussians for all the weights. And then you have an unnormalized posterior, and your sampler, your MCMC approach is usually the tool to get samples from the posterior, because you don't have the normalizing constant as it's usually the case. Yeah. Okay. So in the priors in the weight space is actually something that is well. Oh, good. Yeah. Okay. People would say, for example, this is not meaningful, right? If you're a classical Bayesian person, then this is not only because of the high dimension, but also identifiability problems. Like if you have an overparameterized model, how you're supposed to identify one or the other weight. And then there's work, for example, from Mark and Vincent, who was talking last year. Could be meaningful, but they're certainly not Gaussian. And so on and so forth. I would actually argue that, especially in the case where we have overparameterization, we have prior knowledge, and that's a point that I want to make on the next slide with a toy example, and talking about overparameterization. So I brought 3 networks. The first is just a linear model. It's a 1-1 network. That means your function is defined as f of x is equal to x times w1. This is clearly just a linear model. If you add regularization on top of this, L2 regularization or weight decay, there's no induced regularization, it's just L2 regularization. But now it is a bit different if you take this rather stupid capital L layer deep neural network that has only 1 unit. So it's 1 input, then 1 hidden unit, 1 hidden unit, 1 hidden unit, 1 hidden unit, and so on and so forth. So in the center column here, you can write this down. This is f of x is in this case the x times the product of the capital small WL values and weights. And this, if you define the product to be beta, then, well, you see directly, again, this is just, again, a linear model in the hypothesis space. So we haven't gained anything in expressivity, but we know that if we now add L2 regularization on top, this will induce a potentially non-convex penalty, a 2 over L norm penalty. So the hypothesis space is the same, but the induced regularization is different. And similar for the 1M1 network. So this means I have 1 input, again, no activation functions, m hidden neurons, and one output neuron. I can write this down again. F of x is equal to x times now the sum over capital M products of W1, W2. This is again, if you call this alpha, you directly see this is actually the linear model. And if I add regularization on top, you get a lasso penalty from this. So it's independent of the number of hidden neurons. The reason that I'm showing these toy examples is, well, if you now consider, for example, a function f of x is equal to gamma x, and let's say gamma is 2, you can look into what happens then for, like, what is the optimal weight that you want to find. For L equals 1, the optimal weight is 2, because W1 needs to be just gamma. In the case of L equals 2, WL is square root of gamma, and so on and so forth. In L equals 3, it's 2 to the power of 1 over 3. And then in the limit, these WL guys, these small WL guys, should approach 1 in this case, because as a product, they need to be 2 for this L layer, this very stupid L layer neural network. But that's a bit unfortunate, because we saw before that the regularization actually forces things to 0. The deeper we make this network, the stronger the force, because the stronger the non-convexity of the penalty, the stronger the force to 0. So there's a bit of a mismatch between regularization and what we actually want to get as weights in a neural network. Luckily, this is a very pathological case. If you look into this third network, which is the 1M1 network, you have a sum in there. And so the solution in the limit for every of these weights is 0, or very close to 0, because all of these weights have just to share a tiny amount of the gamma value of the 2 that we had in the example. So they can be very small, and that's now congruent with the penalty. We have a penalty that enforces things to get closer to 0, but on the other hand, also the optimal solutions can be very close to 0. And the lessons learned from this is that networks that can be overparameterized while adhering to the penalty, while not losing expressivity, this is another point that I have not talked about, allow increasing shrinkage of weights to 0. And in Bayesian terms, that would mean we allow increasing prior conformity. So I can show you like a plot for what I mean with this. You see here, this is the sample posterior with a very simple, like a Metropolis Hastings sampler. You see W1 on the x-axis, W2 on the y-axis for different network sizes. And for m equals 1, which is L equals 2 from the example from before, you see this hyperbola, because as a product, they need to be 2. So you walk along this hyperbola. There would be actually another one that the sampler doesn't find in this case, because we have this symmetry around 0. But then for m equals 30, the space that we need to sample from is much nicer behaved. It's centered around 0, and there's no, well, we don't miss out the other half of the space. And you find this, we'll find this phenomenon even in very general neural networks, not just this very simple case. So what you see here is a ReLU neural network, and you see a bivariate marginal posterior point of view. That means you have a large posterior space, and then you marginalize all the other dimensions except for 2. So you look at your posterior like you would look into a window. And if you see structure in this window, like on the left, well, if you see these structures in a marginal point of view, then they need to be also there in this high dimensional space, right? If you marginalize, and so what I mean is, for example, if there's nothing here in the center or here in the marginal point of view, they can also not be something there in the higher D dimensions. So based on, like, this is we sampled here for 10 million samples, so this is hopefully sufficiently explored. You clearly can see the structures in the underparameterized case, exactly in the case where your network doesn't have the expressivity to follow the prior. And then in the overparameterized case, you see like this fireball, which is nicely Gaussian, or looks like a Gaussian, zero-centered, symmetric, and it looks like as if this would be the prior. Yeah.
I mean, the previous one, this is a pretty picture, but I don't trust it. The previous one, it looks like that if you're basically saying that if you increase the number of parameters, you're more free to move around.
Yeah.
But that's not a surprise, right?
That's not a surprise, no.
So you just made your problem harder because you gave it more space to move around. But that means that you also gave more flat space where nothing happens.
That could be, yeah.
Yes.
Yeah.
So then, I mean, you know, it looks like that it's just playing around with numbers, but it doesn't prove anything that all parameterization is good. It's just saying that you have room to move around.
Yes. Well, in practice,
am I right to be skeptic, or am I missing something?
Skeptic about
like you didn't do anything, you were just playing with me.
Well, maybe I come like there's another slide on this for that that will maybe also relate to your skepticism.
Okay.
I don't know.
I understand that the blue one looks bad, right? Because there's not much room to move.
Yeah.
But the red one, just because you have more parameters.
Right.
So that's like a very, without understanding the detail, I kind of go like, oh, of course you increase the numbers, you move more. So it's not like you gain anything just by thinking in this term.
So I would argue that this is maybe something that also comes later, that it's easier to sample from this larger
space, but it doesn't mean that you sample well.
Doesn't mean that you sample well, but empirically you do.
Right. Yeah. I mean, we all were unhappy with when Lapoon in 2008 was saying that you should solve problems like this. And he was saying basically the same thing. And I had basically the same reaction, and I was wrong. So I would like to know if I'm wrong here.
Well, empirically, I think we see that sampling is performing better in this overgeneralized case. Also, the point that I wanted to make here is maybe, okay, I see the point if people say we don't have any, do we actually have priors for weight space? And if the posterior looks like this, probably not. Then our Gaussian priors are, I don't know what it means if the posterior is this. But if we have enough flexibility, then maybe the prior, this Gaussian prior that we assume is maybe not so off anymore.
I would, okay.
Yeah, we can argue later maybe. Yeah. Well, this is already good. Like we started a discussion. So you said you don't trust these plots. Any comments about this? Because it's marginalized over a lot of other dimensions, or?
Yeah, I think I want to look at the paper and then see if this is okay.
Yeah, sure.
It looks nice. So this can be deceptive. Right?
Yeah, again, as I said, like you see structure. If you see structure on the left, if you don't see things around zero, that means something definitely also in the higher dimensions. So again, just the point that maybe the prior is a more suitable thing to do in this overgeneralized model, and that the symmetries happen in I'll get to the point again. And as you said, this is not surprising. There's other literature. This is something that I, not just this year, but also a lot of years before that. Aaron was here, I think, visiting your lab at some point. So I brought this slide up. This is work from Mert Belanchi, who does convexification of neural networks. And what they find is something very similar. They say that if you're at a certain M, then all the solutions are disconnected. If you increase the size of the neural network, at some point things become more and more connected until at a certain point, which interestingly also relates to the number of observations. So this is maybe there's a connection between parameter and data space. You have a connected solution, one connected solution. Then this is another example that shows a two-layer neural network on a UCI data set. And if you look at the product of these two weights, you see that there's a lot of multimodality going on the left, where you just have 8 neurons in the neural network. Same problem, just with 64 neurons now. Everything is now unimodal and zero-centered. And this is a result that looks very similar to a result that was also discussed in variational inference. Thanks for the pointer to Thomas. He pointed out this paper to us by Tripp and Turner, who were talking about a very similar problem, and they said this is actually bad for variational inference, because if we have a lot of these zero-centered posteriors, they argue that, well, then maybe if we find the map solution for this, which is at 0, we prune out a lot of these neurons, and then the super complex neural network becomes actually much less flexible and performs worse than a simpler neural network, just because we have this effect from letting the distributions walk around versus fixing them all at 0. So that there's pruning going on, and then the more complex model becomes worse than the simpler model. In the worst case, they even argue that this induces overvisualization between weights and data.
But it's kind of the same thing again, I think in information geometry, some people know about it. It shows up in terms of Fisher matrix being very diagonal.
Mm-hmm.
Like if you let it be too many numbers to do the same thing, they all have to be very small.
Mm-hmm.
So they all center around 0.
Yeah.
But that's just doesn't mean that you can prune them. It's just that their collective effect is matters, right? Their individual effects don't matter. So they almost also try to behave like they're independent. And some people argue that Fisher is diagonal, and it hasn't worked out well in the past. When if you know the work on natural gradient descent.
Yeah.
So there is an effect. It just doesn't show up if you look in that parameterization.
Mm-hmm.
If you look at too many parameters, everything looks uncorrelated and diagonal.
Yep.
Because everybody can act separately, but there are collective effects.
Absolutely, yeah, I would agree. I also have here that it's not a problem for sampling, but just because they're centered at 0 doesn't mean we don't prune stuff in sampling for this reason. Like we sample around 0, then, but well, so what?
Yeah, I mean, I also think that it's not a problem for variational learning. I mean, that was I think that paper is misguided, is what my opinion is. It shouldn't be a problem if you are careful about how you do inference, right? Because there's too many numbers.
Right, yeah.
Can I potentially comment on this? Yeah. Okay. Can I comment on this? Because maybe we can defer this discussion also more towards the end, because I think there's a deeper connection to this kind of whole theory and overparameterization and the optimization to that. And what you're referring to with the Fisher matrix is likely related to actually the conditioning of the learning tasks, right? So this Fisher matrix has a similar role as the Hessian there.
Yeah.
So it's a conditioning, and you need to be very careful on where you are in the overparameterization regime. What you're saying here right now is what you're describing here, you're close to the interpolation threshold. This is where you roughly, what you were talking about on the slide before, when you get connected. Their optimization is super bad. It's really badly conditioned directly at the interpolation threshold. But it gets much better when you increase the number of parameters even further. And this is likely also what you're going to see here. So you're kind of in this typical statistic regime, you're kind of okay, but your optimization can be okay, but you have fewer parameters. Then it gets really bad at the time where you have roughly the same number of parameters as samples. Then it gets better again. Due to conditioning and some other things I'm happy to comment on later.
Yeah, let's talk about it. Thank you. Yeah.
Great, thank you. Right, and as you also said, this data independence is also maybe worrisome, but here you see some for you probably everything looks yellow. Well,
no, we can see it.
Yeah. So these are correlation matrices estimated from the samples, and actually there's a lot of structure, maybe even more than you see right now with this beamer here. There's a lot of non-yellowish errors, which means there is correlation between the weights. If there would be if you would be data independent, that would mean that our posterior or these correlation matrices should look like diagonal matrices. That's not the case for sampling. All right. This is to sum up this overvisualization part, that suggests that the overvisualization pushes maybe the posterior closer to the phi, at least in the mean, and that symmetries are smoothed out. This is all sort of like a question: does it mean that then, as long as f becomes more flexible, is this in our favor? And is there maybe a trade-off between smoothness and dimensionality? Also, something that maybe relates to your question. The dimensionality is a problem for sampling, and that's why I said I put this last point here, because if now this would actually be the case, if we would have to just increase the number of parameters, at some point this would be very challenging for sampling at least. In optimization, we can also apparently optimize these GPT-4 models that are extremely large, but in sampling we're not there yet. That's why I wanted to talk about sampling, which you also require to make this work. And I brought another toy example. So just consider you sample from a multi-rate Gaussian, the dimension zero-centered. Let's just pretend this would be our posterior, but we don't know, we sample from it. And let's define the radius from 0 as r. You can write down an interesting function, at least for me this was interesting. The total posterior mass is you can define via the radius. So this is here, these two functions are, you can define them as this guy, e to the power of minus r squared divided by 2 as PR, which is the radial density of this Gaussian and proportional to the radial density of this Gaussian. And this here, r to the power of d minus 1 is the infinitesimal volume element of a thin shell at radius r. So essentially, if you would have this Gaussian and you could just look into every different radius and say, how likely is it that I'm at this radius, and then integrate this volume that you have at this radius. And why does this relate now to, well, the difficulty in sampling? You can look into how these things behave for higher dimensions. So these different plots show different PR values, so different radial densities, different infinitesimal volumes, and their product. And this is essentially, for those that do not work in sampling, this is essentially the curse of dimensionality effect. The radial density doesn't move because we're always zero-centered and just multi-rate now. It's also, you can see here that it doesn't depend on d, but the second term depends on d. This is the r to the power of d minus 1. This is just an exponential function in d. And you see that, well, it is constant. This black line is constant for d equals 1, linear for d equals 2, and then, well, so quadratic for d equals 3, and so on and so forth. So this is a exponential function in d. And then their product is this purple, on the slides is more, purple density that tells you where is most of the probability mass in this dimension. So at d equals 50, we should be roughly at the square root of d. So roughly at 7, there should be most of the posterior density mass. This is again depicted here with these contour plots. And so ideally, our sampler should sample exactly on this line here, on this purple line, on this contour line, because there's most of the probability mass. If you would do this naively, if you would, for example, do a random walk Metropolis Hastings, it would try to walk in every of the directions. There was a question, or?
Yeah, they're just wondering if slides will be available.
Okay.
So we'll make them available on the
webpage. So if you would do random walk Metropolis Hastings, it would just walk around in any of these directions. So walk here, up, down here. But you would project most of these directions because they are not close to the typical set. The typical set is, ideally, you want to follow this purple line, right? And so what people do is they, for example, use HMC for this reason. HMC is introducing another auxiliary momentum variable, pi, and defines a Hamiltonian system now that is a function of theta, which is our parameter vector, and this pi, which is the momentum variable. And says that we have to simulate from Hamiltonian dynamics that are given by these two differential equations. You do this in practice by integrating this dynamical system using some integration scheme and then some acceptance or rejection step. So if you're not familiar with HMC, this is not super important. I will get back to these definitions later, but just to define the setup. HMC is in practice not easy to tune. You have tuning parameters like the step size, number of steps, mass matrix M, and there are some trade-offs. If you choose the step size too small, it's accurate but slow. If M, for example, is chosen chosen poorly, then you have inefficient exploration of the space, things like this. And L is also particularly difficult to choose. And that is a real deal breaker in practice. So two smart people, Hoffman and Gallman, came up with the no U-turn sampler, the NUT sampler, which solves this problem. And a lot of smart people, including someone that empty knows, said that, well, this is the only algorithm that technically scales to high dimensions. So what it does is it solves this problem of choosing L by growing a tree, a binary tree, and checking in like backward and forward whether or not we reverse some movements. And then we don't do this. We go like along the tree paths until we would actually, well, before we do this reversal direction movement. And the problem, however, with this NUT sampler is that it requires a lot of gradient computations. That's why this was so slow in the overview slide that I showed before, and the comparison slide. It requires a lot of gradient evaluations, and it is data dependent and not a priori known how many. You grow this tree, which is of size d, and it grows exponentially in d. So for example, if you fix small d to 10, that means that you might need around about 1,000 gradient evaluations until you get one sample. This is very inefficient. You can see this here on this plot. You have different bars, different bar plots for different data sets. The orange line for now is something that you are maybe willing to spend. And then you can see that the amount of gradient evaluations for, in this case, 1,000 posterior samples is much more. It not only varies also between data sets. You see that these bar plots are quite different between different data sets here. But also within one data set, this arrow bar shows you if you run multiple chains in parallel, how long would it take for the fastest chain and how long would it take for the slowest chain. And the difference here is actually 300,000 gradient evaluations. If you would do things in parallel, this would be quite bad, right? Because your slowest chain blocks the fastest chain for 300,000 additional gradient evaluations. So this is something that we tried or wanted to tackle, and a solution to this was the microcanonical Langevin Monte Carlo sampler, short MCLMC, which was proposed in 2024 by Jacob and Urosh, two project partners from UC Berkeley. Urosh is professor of physics, and his PhD student is Jacob. MCLMC is based on another proposal that they had, which is called the microcanonical HMC, which is short the MCHMC. And the difference between HMC and MCHMC is you see here that this is the joint distribution defined by, or the joint density defined by HMC is e to the power of minus the Hamiltonian. What MCHMC does is it defines the joint probability as the Dirac delta distribution of the Hamiltonian being exactly this energy level E that you want to sample from, this outer contour line here. So it says whenever I'm on this contour line, it's 1, otherwise I'm 0. And on this contour line, I'm uniformly distributed. So I'm exactly walking along this line. And you can do this, you can get there by, well, altering the Hamiltonian dynamics on the bottom by adding a projection step that projects the gradient onto the hypersphere perpendicular to the momentum. This way you ensure that you're always conserving energy. And what MCLMC now does, in contrast to MCHMC, is it has another Langevin type of stochastic term here. This is a Wiener process here and some tuning parameter eta. So MCLMC has quite some advantages over HMC and NUTS. It does not require full momentum resampling. It does not require this like what is typical for MCLMC algorithms, a metropolis adjustment step. The gradient emulations are deterministic instead of like varying, as you saw before. And under certain assumptions, the ESS, the effective sample size, can be shown to be constant for MC-LMC with respect to the dimensions, whereas for HMC, it's decreasing with the number of dimensions. And so what you saw before, this comparison, the red line is actually mild. This is our approach, which is based on MC-LMC, whereas the other plots here, the other bar plots, were this BDE approach, which was not spaced. So essentially, well, the difference between the bars and this line here is what you save in gradient evaluation. Right. So that was the ingredient for success for sampling, but you need optimization still for this. So BDE and MILE both have the similar idea. They combine deep ensemble and some sampling technique. This gives you a nice exploration-exploitation trade-off. You do the optimization to go somewhere in the space, and then you sample around the things that you found with the deep ensemble and do some exploitation. Most importantly, however, it does not require the sampler to walk in this very complex loss landscape, because the sampler is not really, even MC-LMC will not be able to do that well. To demonstrate this, here is sampling with and without optimization. So if you would just run HMC, NUTS, and MC-LMC on a task, concrete or energy, and would count or compute the proportion of meaningful samples, meaning samples that are not NaN, samples that are maybe better than a constant model or a linear model. These proportions are very small for HMC. 3% would be meaningful samples. This is not very effective. NUTS has a higher number, 14 and 31, but also not super large. MC-LMC is also rather small with 20%. But if you would use any of these sampling routines and do optimization first, you get to 100%. Like all of the samples that you generate, at least in the cases that we looked into, this is also, I think, based on MC-LMC or NUTS, so one of these, maybe not in all the cases, but in our examples, all the samples were meaningful. Like the sampler doesn't get stuck somewhere because you do the optimization first, you walk somewhere meaningful, and then you start sampling. And here's the process, how this looks in practice. So this 3 steps, three parts in this whole process. You first start sampling, and you improve in the LPPD because you're optimizing. Well, if you just do optimization, you improve the likelihood, not the LPPD. Then you're here, and then you do warm up. Warm up is well, something that you, for example, do in NUTS. You try to find a suitable mass matrix, for example, for the momentum, and then you improve in performance already. And this part we interpret as moving from something that is closer to a map solution to the typical set. So that's at least our interpretation why we're improving in LPPD. And then after you start sampling and you improve further in performance, and that you do because you do Bayesian model averaging. You average a lot of these hypotheses. All right, so this is essentially the broken down and simplified the yeah.
What data is it?
Second?
What problem this is? Like what model data?
This was again a UCI data set. I don't know exactly, and a multi-layer perceptron. Would you
like the baselines? Where do they stand in this one?
The baselines. I would have to look it up. I don't know exactly, but it's not that we have not tried to optimize this here. So I think this is performance that is reasonable. It's like for example in the tables that I showed at the beginning. The deep ensemble performances are something that you will also see in the literature, and then still adding sampling on top, you can gain something from this. In LPPD, I'm not saying other metrics.
Yeah, like if I did the variational mean field something, do I see it around 0.4 or do I see it around 0.3?
I mean, we can briefly check.
It's okay. I don't want to derail your presentation. Please, we can talk about it later. It's okay.
Yeah, I mean,
It's fine.
Yeah, you're the boss.
No, you're the boss. You're the invited speaker. So you do whatever you want to do, please.
Okay. I mean, how much time do we have left? I think.
5 minutes. So you started around 5 minutes after. So it's about an hour. So you've got about.
Okay, I can do the rest in 4 or 5 minutes, and then we have still time to discuss. So maybe some implications now having this procedure in place. What can you maybe learn from this? So maybe I start with the priors because that's something that at least we found to be interesting. Usually we use these standard Gaussian priors and looked into, like this is an excerpt from a benchmark study, what prior scale is usually working the best. And the interesting thing is not that we are centered around 1 roughly, so maybe the standard Gaussian even is something that is meaningful, but that the parameter sizes do not really matter in terms of this LPVD ranking. So no matter if you're in a 200 parameter setting or a 1000 parameter setting, these performed similarly well, suggesting that, well, this means that we have induced more regularization. We increase the network size, but then on the other hand, also we induce more regularization, which makes sense if you think about this introduction example that I gave. Scale independence implies more regularization for larger models. A second implication is symmetries. So I was suggesting that there's maybe less structure, less symmetries in if we do overproducing. We try to check, for example, now, do symmetries influence our sampler? How can you do this? Well, you can maybe try to generate some of these symmetries. One option is, for example, permutation symmetries. You optimize your model, and then instead of optimizing it 10 times to get 10 starting values, you optimize just one model. You permute your one model in the weight space, but keep the function space fixed. So you just switch up neurons. And then you can check how well does the performance do if I start from permuted to warm start. So all of these blue lines are different chains, and the red one is their ensemble performance. And all of these blue lines started from the very same optimized model. They were just permuted weights. And you see that they perform similarly well to regular warm starts. So we don't see a lot of difference, suggesting at least that the permutation symmetry in this case doesn't really matter that much. There are other examples. I have something in the appendix also for other symmetries. This was just a glimpse into the results. About the shape, I think we discussed this already before. There was it depends on the parameterization in the prior, and the question is, does everything turn into this Gaussian fireball? Is this just maybe, well, maybe this is just visualization? The answer is no, it doesn't. Not everything looks like a fireball. You have this Sauron's eye here, or the coffee mug effect here. So these are bivariate marginal plots for the kernel and for the biases of selected kernels and biases of a multi-layer Bayesian neural network. And the interesting part is this aligns well with, for example, also sparsity neural networks, that the hidden layers are sort of look more Gaussian-like, are more zero-centered, have less structure, whereas the first layer where you likely learn most of the features that are important, and the last layer where you need to combine them, they have very particular structures that are not zero-centered, that are not symmetric, that don't look like your prior. And this is even the case even if we overgeneralize by a lot. So you won't get these fireballs in the first and the last layer, because you need to learn these specific structures that depend on the data in these layers. And last but not least, I wanted to make this even like this part. I was hoping to have even longer because this is something that is also particular to sampling. If you read about sampling-based inference, you oftentimes read that people use this as a ground truth. But the fact is that not only does every sampler differ in its efficiency, but also in the way it approximates the posterior. And this is a very interesting result here. You see here 4 different plots for 4 different neural networks. You see on the x-axis the layer index, so 1, 2, 3, 4, so how deep you are in the neural network. And on the y-axis, you see activation rate. These are ReLU neural networks, so how many of the neurons are active. And what you see is that if you do a map estimator, you're around 50% neurons are active. If you use a NUTS-based sampling routine, it's a bit smaller, but also around 50%. But then if you look into what we use, the MCLMSC-based sampler, you see that the activation rates are decreasing consistently over the different layers. So the further you go into the network, the less activations there are. And the gap is quite large compared to the other sampler. So both samplers, NUTS and MCLMC, are supposed to sample from the same true posterior, right? But then apparently they have some inductive bias, some implicit regularization going on because they behave quite different in the activation patterns. And well, I cannot go into more details, but the point here is that not every sampler is like gives you the same posterior. They are different, and they are different because the way they sample. They have some induced regularization or induced approximation. All right, so I will wrap up the talk. Current bottlenecks for our approach: large-scale data sets, large-scale parameter space is always a problem. We try to tackle this to some extent with this approach. What is particular to sampling is the inference cost. So this is something you don't have in optimization. And that's also something that I found in last year's Bayes-Duality workshop talk from Professor Lee, who is telling the exact same thing. If you produce 1,000, 10,000 samples of these weight vectors, you have to store them somewhere. And if you do inference, you have to process them somehow, right? And that's something that is very costly. Professor Lee provided some distillation approach, I think, as a result. But that's something I think this is still not 100% solved. So as a summary, I brought a quote from Ismailov and Wilson's paper. They said that back then, to scale HMC for the modern problems, they use 512 TPUs. Next year, it will take a day to run on your computer, hopefully on your laptop. So this is something that I think I'm pretty excited about. What has changed? Well, they use JAX already, but there's also the Blackjack software for sampling. I've not talked about this. This is also part of the solution. The methodology combining optimization and sampling, I think this is the way to go for sure. Efficient sampling was the third component, so using MCLMC. And then MILE, which I also haven't talked about, is something that is a tuning-free approach, which also helps a lot in practice. So to summarize the lessons learned, overprioritization can help maybe, I don't know, we need to discuss. Implicit regularization by the prior architecture sampler maybe is something that is relevant for these cases, and symmetries might not seem to be that big of a deal breaker as maybe was thought recently. Thank you very much.
Thank you. So we have time for just a few more questions, preferably not for an MT first.
Not from MT first.
Thank you for the talk. The plot with the posteriors in the hidden layers, could we say that this is exploring more the solution found by the optimizer rather than the kind of true posterior? Because you do this warm starting with SGD or Adam, and then you do something around. So is this maybe not really the neural network true posterior, but rather what Adam finds? And if we would use a radically different learning method, maybe these things would be, let's say we do RBM pre-training or something, and then from that pre-trained solution we would run the sampler. Maybe these would look entirely different. Like, basically the question is, how much does this depend on the optimizer?
Yeah, that's a good point. I think in this case, actually, so we would have to compare different optimizers as a warm start and then see how this differs. But I think, so these are 10 million samples from, well, it's 10,000 chains, but it's still, so it's 100 samples per. So I think this is still reasonably a lot to say that, well, we have maybe, so if we do a warm start like this, our posterior will have a bias from this warm start for sure, but at least our hope is that this has become, like, if you sample infinitely many samples, then it should be not relevant anymore, right? And our hope is that it has already faded out, but yeah, I cannot say for sure whether this is the case. Yeah, good point.
Thank you.
Many things. I have a question regarding the efficiency. So first of all, super inspiring talk, really cool. Do you have similar concerns about efficiency in sampling as you have in optimization? So maybe because of the warm start, but also like, what is unstructured sparsity, for instance, having you, or there's a structured sparsity? Because you showed that your kind of efficient sampling technique would actually bring the activations down, meaning like it implies some form of structured sparsity that you could exploit at least at infant stages when you need to evaluate the model. But at the same time, do you care more about the number of parameters? Also, would then unstructured sparsity help you? Because in that case, I would assume you could get rid of a lot of things just by randomly dropping also some of the parameters, because you have this parallel potentially also to when optimization works.
Yeah. Okay. So these were, I think, a couple of questions. So what we tried, based on, for example, this result, is to say, okay, in the hidden layers, it apparently doesn't make. Maybe it's not super important what exactly we learn. The important thing is that we learn something like a feature map maybe in the first layer, and then to combine it in the last layer. So you could, for example, this is something that was done in the Bayesian neural network literature before, last layer inference, or maybe keeping certain layers stochastic and some not. Like this is work by Eric and Tom, I think. First layer, last layer stochasticity, and the rest is fixed. I think they perform reasonably well, but then, yeah, I mean, there's some doubts to it. No, I mean, I mean, in this case, so your question was, can I reduce the complexity of these networks, because it seems like, or
yes, but also what are the factors that you care most about at this? So do you need to be fast, for instance, in evaluating in your network with sample parameters, for instance, or is the inference doesn't need to be fast? Do you only care about the number of parameters? Do you care about specific structures in the architecture? So having lower width, for instance, or lower depth is helping you much more, something like that? So
in this case, I think we want to gain efficiency for a given architecture by, so the point with the open parameterization in the beginning was we potentially make the space smoother and easier to traverse, and therefore we are more efficient in the sampling.
So fewer sampling steps potentially.
Fewer sampling steps, yeah. Effective sample size means that how often do you sample and how much truly uncorrelated samples you get from this. Yeah.
Yeah.
Okay.
But does it also depend on the architecture itself? Because you kind of, it sounded like that, especially you cared about the number of parameters when you were, discussing the D kind of in the dimensionality when you were discussing the, basically the. So the point that we're discussing D here is that usually we'll have like in the second last point. Efficiency losses if D becomes large. So for the very simplest case here with the random walk metropolis Hastings, essentially if it's only like a couple of dimensions already, just because of the pure probability that you search into another direction, you reject the sample, meaning you do an evaluation, but you don't take the sample into account into the sampling pool because you say that this is not close to my posterior.
And then you do a lot of computations, but you actually don't add samples to your bucket of samples. And
but these would be the number of parameters of your network.
Yes,
right?
yeah.
So having fewer number of parameters would help you potentially.
If you're able, right. If you would be able to run in the dimensions of the relevant parameters, these maybe less efficient sampling routines, then they would be they would be much more efficient. Yeah, right. So I think this is also something that is currently explored, for example, in subspace inference. So people look into subspaces and then try to sample there, because there it might be actually feasible to do these other sampling routines. Yeah.
Cool. Would you allow me also one comment, and then maybe we'll talk about someone else, but one comment on the parallel, that you were caring about, André? Yeah. Is it okay? Because you were kind of concerned about this question, like whether when you increase the overparameterization, whether that would actually help you with the sampling, because you increase the space of possibilities, right? But there's also this result in overparameterization, where people, they wonder, right, why overparameterization effective with optimization. And one hypothesis is that it has also some good theoretical background, or founding, is that somehow the likelihood increases that you initialize your neural network close to an optimum already. So you only need to do a couple of so basically you can also converge faster in SGD. And it sounds to me like that the number of I think along the chain, probably the chain length or something like this, is likely kind of related to the number of SGD steps that you need to do. I would think so, intuitively, something like this. So, or at least, it increases the probability that you start already from something that's relatively good. So maybe, more closer on your actual ring. And the same principle should then also allow you to converge faster in something. Just a hypothesis, but there is good theoretical backup for this.
I mean, yeah, a good point. So I think in general, a lot of things that apply to optimization also apply to sampling efficiency. So if you're, for example, have like an ill-defined problem, large curvature in one direction, low curvature in the other direction, this is very difficult for even more sophisticated samplers. So if you're able to improve that, then your sampler will also be more efficient. Yeah, and maybe that's a point that could be.
Principle that to partially explains that. Absolutely.
Yeah.
All right, let's thank our speaker one more time for a wonderful talk and discussion.